Thanks. Okay, I think we can get started. Yeah, right. Okay, today we're going to finish up emerging memory technologies, which we covered mostly last week. And then we're going to start more about memory controllers, especially memory scheduler design, focusing on quality of service. Any questions before we start? Yeah, there will be a lab on memory scheduling later on. Remember, we discussed opportunities with emerging memory technologies. We were talking about especially resistive memories, and we talked about processing tightly coupled with memory. And here, in addition to being able to do block bitwise operations, resistive memories enable another opportunity, which is cross-bar array operations, matrix vector multiplication, which is quite interesting. But we also discussed that this is an example of processing using memory. You're really using the operational properties, analog operational properties of the memory substrate to do computation. So there's more to come in this area, I believe, but we're not going to talk about that. And we started talking about merging of memory and storage. This is another opportunity that's enabled by memory technologies like what we have been examining. And this is a slide that I showed, but I wanted to show it again. Basically, the storage and memory hierarchy got decoupled over many decades because of the way devices have been. So hard disks were extremely slow, as we also discussed, and DRAM was quite fast. Can you guys fix this waiting room? It disrupts the presenter. This is a pretty bad user interface design with Zoom. We cannot control. I don't know why they do that. I mean, okay, let me derail here. Why would you ever disrupt the presenter with something like this? I don't know. If you design software, please don't do it. And I see a lot of problems with software. Like I use the SBB app, it's kind of useless. Or ZVV app, it's also useless. Now what this ZVV app decided to do was basically because the time changed, right? We went from Central Eastern Standard Time, Central Europe Standard Time, to Central European Time. Now it tells me that your time has changed. So it got stuck in 30th November when the time was 30th October when the time was changed. So basically, in all of the software design, people somehow are not rigorous enough. They're not testing, in my opinion. I think if people test these things on themselves and think about these corner cases, they can be much better software designers. And we think that we're going to really do self-driving cars. What do you guys think? I don't know. I'm just joking, of course, but I think if we don't solve these very basic issues, I think we're going to have a lot of trouble going into space or doing self-driving cars, etc. So this was another example. It looks simple. It looks like I mean, you may say that I'm petty by bringing this up, but this is actually a fundamental mindset issue, in my opinion, right? If you actually decide to disrupt the presenter just because someone needs to be admitted, especially when there are other co-hosts in the Zoom meeting, yeah. Anyway. So think about the design choices you make when you're designing hardware or software, basically. A lot of you may not become hardware engineers. Some of you will become software engineers. And this is why you need to do things in classes and you need to test your systems so that when you go out into the real world is real. Here, you're doing simulation in classes, right? This is not real. But once you go into the real world, you're going to interact with users. You're going to design systems that are going to be safety critical. And you cannot basically cut corners there. You can cut some corners as long as you don't affect something really important, but people will be annoyed at you. And worse, people may die because of your design decision. So think about that. That's the bar, in my opinion. And that's the role of education, in my opinion. The role of education is really to convey the importance of what people are doing and what people should be doing to actually design better systems in the world. Okay, that was Zoom interruption. So we got interrupted based on that. Now let's go back to the what we were doing in the main thread, let's say. So basically, the storage and memory subsystem evolved because hard disks have been extremely slow and DRAM has been quite fast. As a result, and also this is persistent, right? And block addressable. Whereas DRAM is clearly fast, volatile, byte addressable. So persistent data goes there and volatile data goes there. And you want to manipulate some persistent data, you first bring it into DRAM by doing memory mapping and then write it back into hard disk. And if you get some crashes in between, you need to be very careful, basically. You may lose some data. So there's an issue here. If DRAM is not persistent, you may actually lose some data when you get a crash if you haven't reflected the updates in DRAM in your hard disk. So today's systems are actually vulnerable to this. If you really want to design a reliable system, you need to think about this, basically. We're not thinking about it clearly in this course, but you need to think about it. So what non-volatile memory technologies enable is they basically sit in between DRAM and hard disks. They're fast like DRAM, close enough, byte addressable like DRAM, and non-volatile like hard disk. So it doesn't have the disadvantages of hard disk. It has a lot of the advantages of DRAM, except what we have discussed earlier, right? So this enables us to rethink how our memory and storage hierarchies should be designed, perhaps. If you actually replace the storage device over here, I don't know what happened over here. Yeah. Oh, okay, I removed the animation over here. If you actually replace the storage device, hard disk, with phase change memory, for example, the access time to the slow device, or basically if you actually, I shouldn't have removed the animation over here, but if you actually had a hard disk over here, the way you access the hard disk is actually quite slow. You basically go through operating system calls and file system calls to map the data that you're accessing from the hard disk into the main memory. And that requires data movement clearly from here to here. And then when you actually, and then you do the manipulation over here, and then you write the data back over here. And if you're actually opening a lot of different parts of a file, this could actually be a huge bottleneck. The way it's done in today's systems is the storage device, the hard disk, does a DMA, direct memory access, and writes the data to main memory after the CPU sets it up. CPU basically says, hard disk, you write this data here. And the hard disk actually has access to the memory controller through the interface. And that memory controller, the DMA engine, direct memory access engine, and the memory controller writes the data to main memory. So we're going to talk about that later in this lecture. Clearly, the hard disk access also go through the memory controller. So that's interesting, right? We will see that. That's going to cause interference to the CPU over here as well. But let's assume that this device became extremely fast, like phase change memory, then this becomes a bottleneck. Basically, the operating system and file system calls to open files, map files, manage files becomes a bottleneck. And I'm going to show you how bad of a bottleneck that is. So does it really make sense to actually go through this sort of interface to access persistent data? And one idea, which is actually an old idea, that's not a new idea necessarily. In the 1960s, we had single level stores because there was not a huge, actually 1950s, 1960s, we had single level stores because we didn't have this dichotomy in the memory hierarchy. We didn't have DRAM, we didn't have SSDs, we had something called core memory, and that core memory was magnetic and everything accessed there, it was persistent. Essentially, it was a single level store. You accessed everything with loads and stores, and then over time, file system interfaces and memory interfaces got diverged from each other with the development in technology. So DRAM was developed in 1965, as we discussed, right? And hard disks also came about around that time. Okay, so if you actually have a single memory technology that actually is good at everything, like we kind of see over here, we're going to change that also a little bit, but why not actually have a single interface to manipulate both persistent data and volatile data? And this way you can eliminate wasted work to locate, transfer, and translate data. So if you actually have two interfaces, and if you need to decide where you're manipulating the data, you need to have mapping mechanisms to decide where your file is. Is your file in hard disk or is it mapped to main memory, for example? So that manipulation requires mapping mechanisms and translation mechanisms and certainly transfer mechanisms to do that. But if you have a single device, a lot of that goes away essentially. This improves both energy and performance, as we will see in a little bit. This also can simplify the programming model as well. Wouldn't it be nice actually if you got rid of the file system interface completely and used loads and stores directly from your programming language to manipulate persistent data? So you have some persistent array, for example, and you basically store to it. That'd be nice, right? You don't need to go through files. That's the idea over here. So persistent memory provides an opportunity to do that, essentially. And this is an example. Of course, unfortunately, it's not just persistent memory, right? We just discussed in an earlier lecture that we cannot eliminate DRAM completely because it has a lot of advantages. So in today's world, we cannot just get rid of DRAM. So we may add phase change memory, STT-MRAM, etc., and we have flash, hard disk. This could be your memory space. This could be your memory and storage space. And this could be managed by some hardware software cooperative layer called persistent memory manager, which actually does a lot of actions over here. I'm just going to give you the idea. I'm going to leave some of the details to papers that I will briefly mention. But this could be the programming model, for example. You could have a persistent array, declare it as persistent. File could declare it as persistent, but it's not really a file. It's really an array. And then your updates to that array can be persistent. And there may be some software layer that guarantees where this data is placed underneath because you marked it as persistent data, right? So this is an object-based interface. You have persistent objects, but you could also potentially translate existing file system-based code to something like this. And people have been working on that. Okay, so the idea is to use access and hint information coming from the software and also collect it in hardware over here. Well, hardware part of it over here, to allocate, locate, migrate, and access data in this heterogeneous area of devices. So for example, if you figure out that a data has to be persistent and it cannot be mapped to DRAM because it's really security critical, because if you actually lose an update over there for whatever reason, in a crash in space, for example, you will actually have some huge safety problem. Then you basically say it's always allocated in NVM and you directly access it from the NVM. So this enables that sort of behavior, which is very difficult to do today. Today, you go through a file system interface, right? And you're basically bound by what the file system does. Here, the goal is to strictly specify where something may be allocated. And if it's not important for the programmer to allocate something to a particular device, then it can be managed by this persistent memory manager. Okay, so I'll give you the key ideas. This is a paper that describes the vision, if you will. You expose a load store interface to access persistent data. That way, applications can directly access persistent memory. There's no conversion, translation, location overheads for persistent data. There's just the overhead of the persistent memory manager, which could be big if you don't design it carefully, of course. And then it manages data placement, location, persistence, and security. This is a lot to say, of course, but this is important to do, basically. Depending on the characteristics of the data, you need to decide where to place it. And this is actually an important research direction, clearly. And this is kind of very in line with what we have discussed in this course, hardware-software cooperation, right? Who decides what should go where? What kind of properties can be discovered dynamically? What kind of properties cannot be discovered dynamically? So persistence and security are very difficult to discover dynamically. So you may need some programmer hints, for example. But performance characteristics, you may actually discover some of those dynamically, right? It manages metadata storage and retrieval because this you still need to have some mapping mechanisms to decide which data should go where, especially when you're optimizing these. And finally, it exposes hooks and interface for system software as well as applications. This enables better data placement and management decisions. I'm going to give you an example of this, but this paper and other papers that came after it describe some things. So any questions so far? Yes, please.
Previously, we mentioned data memory controller, and that is more like a device level. And this one is more about, is one layer up, right? It's allocating different data. It's not really changing the device like latency or refresh rate.
That's correct, yes.
It's one layer up.
You can think of it as one layer up, yes. Yes, exactly. It can still do what we had discussed earlier, but it's still maybe at a lower layer. It could be part of that, but it's really a one higher level abstraction. You're right.
Like it knows better what the software is doing and allocates according to the type of the data.
Mm-hmm. Yeah, exactly. But you still need to know about the device characteristics to decide where to allocate, right? So you still need to know some information about the device characteristics.
So you mean it can still adjust the device refresh rate or some errors?
I believe so, yes. So in the end, I agree that sort of management is a lower layer, but you could combine it with the information coming up from the higher layer also. So if the software says, for example, this data doesn't need to be refreshed because I'm going to touch it quite often, that could be a hint. That could also be used to manage the adjust the refresh rate potentially for that particular piece of data.
But then it's multiple kinds of memory latency device.
Yes, it could get complicated. Basically, this can combine a lot of the ideas we discussed, but I'm not going to combine them right now. So yes, what we are discussing here is at a higher abstraction level right now. Any other questions? Okay. So basically, if you think about it, this single level store exposes a large persistent address space, but it may use different devices to satisfy that goal, right? Depending on the data characteristics. It can use anywhere from DRAM, which is fast but low capacity, and then it can use high capacity but non-volatile hard disk drives or flash and other NVM devices in between. It can even use tape, right? In fact, I think the vision can be even broader in this. If you think about, I think this is a bit hard to implement, but if you think about the world, you can think about everything as addressable, right? If you want to, let's say, communicate with that window over there that has some address, and that could be, if you want to put some data on that window, don't laugh about this because people are actually trying to build glass-based storage. Not exactly like a window, but it's glass-based, some sort of glass. So you can think of devices all over the place, and you can have interfaces you can have a single interface to manage all the data that you have, including the network. So here we didn't include a network over here, but a bigger sort of vision could actually include the network. That way you can actually access some other devices that are out there. So basically the idea is actually much broader, but we're going to restrict ourselves to memory and storage devices. And performance energy can benefit from good data placement across these devices. You can utilize the strengths of each device and avoiding their weaknesses. Let's take a look at two important application characteristics, locality and persistence. So simply, a programmer may think about marking the data structures, right? So locality may be high or low, and persistent you may have persistent requirements, but data can be temporary. And let me give you some examples. I mean, this is, you can actually, when you write a program, you can usually easily identify where you sit in this, which quadrant you sit in. So for example, a columns in a column store in a database that are scanned through only infrequently. It's probably persistent data because you have a database, right? And you can place it on flash because you're streaming through the data because you don't have a lot of locality. And as we discussed in the last lecture, you can make streaming accesses very fast in many, many memory devices. In fact, if all you're doing is streaming from memory, you can design your system for streaming such that you have enough buffering, right? You have enough bandwidth coming out of the device, but you have enough buffering so that you can tolerate the latency of streaming. Random access is much harder, as we discussed last time, right? Once you go to random access, you're really exercising the latency of memory a lot. So your banks, your individual memory accesses need to be low latency because there's no easy way of tolerating those random accesses, right? Whereas streaming, you know what you're going to access, you can keep prefetching, right, from the device. As long as the device provides enough bandwidth, streaming is easy, I would say. Random access is really the hard part. So this is an example where you can mark the data as persistent, but not so much locality needs, at least temporal locality needs. So you can place it on flash, for example. In fact, you could potentially place it on tape, but that requires a little bit more better prefetching, let's say. Okay, another example, for example, if you have a frequently updated index for a content delivery network, you need to have the index so that you can decide where to serve the request from. This doesn't need to be persistent because you're really changing where you serve the request from. But this has a lot of locality, hopefully, if you design the index well. As a result, you may want to decide to place in DRAM, right? And then there could be other things that you can imagine, right? So applications or system software can provide these hints for data placement. That's the idea over here with heterogeneity. So it's a little bit different from what we had discussed earlier. Earlier, we we're looking at just performance characteristics, right? Now we're talking about persistence as well as performance characteristics. You can actually enhance this with more dimensions, but as you add more dimensions, it becomes harder and harder for the programmer to reason about. But there may be ways of actually discovering this information over time. Yes, please. So here you're really marking the data structure. So it's essentially data structure granularity, the way we have envisioned it. Yeah, yeah. Because the dynamically the behavior of the program. Yeah, no, yeah, you cannot do this at the program. You really need to identify the different data structures. Okay. No other questions? Okay, so let me give you, so these are some ideas. There's a lot more other stuff that we can discuss, but we really don't have time. I'll refer you to that paper that you can review also. But let me give you the benefits of doing something like this in a very simple way. So we're going to evaluate several systems. One is the traditional hard disk baseline. You have a traditional system with volatile DRAM and persistent hard disk. And this unfortunately has the overheads. This is a two-level store, overheads of operating system and file system code and buffering that we discussed when you decide to manipulate files. We're going to look at an MVM baseline. This is very similar to phase change memory. It's same as hard disk drive, but hard disk drive is replaced with phase change memory. It still has the software overheads of operating system and file system. This basically says, okay, I did replace the hard disk with phase change memory. What kind of benefit do I get? We discussed this last time. Basically, we were discussing replacing flash, for example, or replacing storage with phase change memory. Unfortunately, we don't have the evaluation of flash, but I'll kind of point you where it could be in the pictures. So there should be another evaluation over here with the flash baseline and then MVM baseline, but we don't have it here. And then the persistent memory, what it does is it uses only non-volatile memory, no DRAM. Basically, it gets rid of the DRAM in these two systems. It replaces, essentially, it gets rid of the DRAM, and it uses loads and stores to access non-volatile memory. Basically, it gets rid of the operating system and file system overheads to manage the data, persistent data. So this is the system that is a single level store, if you will, but it doesn't even exploit the heterogeneity of DRAM. So data is manipulated directly on the non-volatile memory device. And non-volatile memory is slower than DRAM. It's about 4x. We use the same latency parameters that we discussed in the phase change memory paper earlier. It's about 4x slower. So we're getting rid of the fast memory, but we're also getting rid of the software overheads of managing persistent data. So let's take a look at the performance of these systems. This is on one application, but the paper has many other applications. So if you look at the hard disk, and these are on storage intensive workloads, essentially, you're manipulating a lot of persistent data. So you can see that the hard disk is really dominated by the disk drive latency. If you replace the hard disk with something like phase change memory, you get a huge performance improvement, about 24x. So as I said, flash, we didn't evaluate, but I expect flash to be somewhere over here, actually. That's why flash is essentially everywhere today, right? Because it has enabled a memory technology that gets you over here. Okay. So this is huge. Now, if you look at this two-level storage with non-volatile memory, it has DRAM and non-volatile memory. If you get rid of DRAM and manage everything with loads and stores with a single interface using non-volatile memory, you still gain 5x performance improvements. So you basically got rid of the fast memory, DRAM. Everything goes through slow memory, which is phase change memory. But you also get rid of the overheads of management. So that gets you 5x. So it's actually quite good. And that's what we would like to achieve with a single level store. And now on top of this, you can actually add hybrid memory and you can get the benefits that we have discussed in the last lecture. So if you add the DRAM and manage things, you can actually get much better. And a lot of works actually have seen that. Any questions? Yes. So why do you get the benefit? Basically, this here in the NVM, the real bottleneck is all of those system calls that you do. So to manage the persistent data, file accesses, you need to go through the operating system. NVM devices on the order of 200 nanoseconds, right, to access. Okay, say 300, 400 nanoseconds. But the system calls are at the microsecond level. So you're basically paying a lot of microsecond level latency costs to access the non-volatile memory device. We're getting rid of all of that latency. We're essentially managing NVM just like DRAM, just like we talked about in the prior lecture. Make sense? Yeah. So that's the importance of optimizing your software stack. Earlier we discussed it. other ways of optimizing your software, but it's another way of optimizing your software. So I think the takeaway over here is, if you have a fast device, don't slow it down in software. Access it as fast as possible. Get rid of all the software overheads to access it. This is actually a recurring theme. People have figured this out in Flash, for example. Flash memory is not extremely fast, clearly, like DRAM, but it's quite fast, reasonably fast. People figured out that if you actually treat flash memory just like a hard disk drive, you have a lot of software overhead. So there's a lot of research that shows that you could get rid of the software stack from flash memory and make the system much faster. Some of those techniques are employed, I believe, in things like this, where people can actually integrate across the hardware-software stack. They may not be employed in other systems where you don't have the luxury of customizing your software to your SSD, basically. So if you're designing your SSD as well as your software, you can basically access flash memory really fast. But if you're buying your SSD from someone who doesn't care about your software, it's a very general interface, right? You cannot optimize those things. So it's good to think about some things. If you're a vertically integrated company, you can actually do a lot of those optimizations to access a fast device really with the latencies that's close to the device latency. Ideally, you would like your latencies to be close to the bare metal latency that's provided by your device, and you should not add any overhead to the software, right? Yes. Yes. So here, you should read the paper for more detail, but basically you have DRAM and non-volatile memory, and there's a management mechanism that decides where the data is. So DRAM is used as a cache, essentially. So DRAM caches the hot data. So you get low access latency of DRAM, hot and not persistent data. If you're manipulating persistent things, you have to go through the non-volatile memory and put it into DRAM and then do the manipulation. Mm-hmm. That's correct. Yes, that's correct. Yes.
And then if you remove that, like, sort of more EMA,
yeah, there could be other performance gains that can happen here, certainly. No question about that. But that could apply to a persistent memory system that also has DRAM, right? That's why we didn't do a lot of optimization. This is just to show that even if you remove the fast memory from the system, if you remove the software overheads, you get 5x performance improvement. That's the idea. You can employ many, many other optimizations here, right? And also here. Okay. So energy benefits are also commensurate. This is if you go from hard disk, if you replace hard disk with phase change memory, you get 16x energy reduction. And again, flash is somewhere over here, which is a good thing for flash. And if you actually do what we just said, get rid of DRAM, but also get rid of the software overheads of managing persistent data, you get about 5x energy reduction. And this is, of course, this depends on the application, right? This is a storage intensive application. If you're not manipulating any persistent data, you should not see a whole lot of benefits over here. But real applications that benefit from large capacity memories usually manipulate a lot of persistent data. Okay. Any other questions? These are good questions. So I like this sort of lectures because this really enables us to rethink the inefficiencies in our systems, right? Some things are, I mean, there's a lot in the research community that actually is thought about in terms of how to get rid of the overheads of flash, for example, how to get rid of the overhead of software management of flash. But unfortunately, some of those don't make it to our real systems. And the reason is, again, if you go back, it's really the partitioning of the industry, let's say. There are people who design flash devices, and there are people who design CPUs. And because there's no cooperation, and there are people who design software, if those are designed by 3 different people, the optimization potential across those gets close to very zero, essentially. You're basically bound by the interfaces between those devices. And those interfaces usually don't communicate enough information to co-optimize. But as I said, if you're vertically integrated, you're designing the software, or at least kind of dictating most of the software, and designing the hardware, designing the CPU, as well as designing the hard disk, then you actually can do a lot of optimization. Now, the downside here is DRAM is not designed by the company that designs these things, right? Well, this is Apple phone. There could be Android phones. Then you're back to square one, which we're discussing, right? Because with an Android phone, you're back to square one, essentially, right? Unless Google is doing a lot of optimization across the stack. But then that requires Google to do those things, or Samsung to do those things. Okay. Any questions? Yeah, this is a paper we wrote about this in about 10 years ago. You can read it. It's more of a position on what should we do to get rid of the inefficiency in the storage and memory hierarchy. I think there's a lot more to do in this area. Also, not to mention that this is also another paper that has Intel and AMD in both as co-authors. That doesn't happen very frequently. Okay, so this is basically the challenge and opportunity. I spent more time than expected over here, but I think this is an important challenge and opportunity because we have a huge inefficiency in that part of the system, memory and storage. And the question is, can we have a unified interface to all data, starting with memory and storage in a single node, and then maybe you can extend it to many nodes. Now, the good news, well, or bad news at the same time, is people have been working on this. I think Intel Optane persistent memory is an example of this. It was a step in the right direction. We'll see where it goes. Maybe it will not go anywhere for some time. So, but hopefully people will be doing research in this area. And again, combining it with processing inside the non-volatile memory could have been a next step. And I believe it will be a next step in the future, but we'll see when it will become commercial. We don't know, of course, right? The good thing is people are trying. Okay. Let me give you another challenge in persistent memory. I'm not going to go into a lot of detail over here, but this shows you another challenge in adopting these things. And this challenge is ensuring consistency of the system and the data if all of your memory is persistent. So basically, you're manipulating everything in the persistent domain. Think about this. What happens if the system crashes? You can basically say, let the system handle it, make everything programmer transparent. This actually imposes a huge burden on the system, as we will briefly discuss. Or you can say programmer handles it. Programmer needs to rewrite their code to make sure nothing bad happens when persistent memory is the only type of memory in your system, and you're manipulating persistent data structures directly. And when system crashes, for example, there's no problem that will happen. So there could be many alternatives in between, and people are exploring the space. So let me give you an example here. Let's assume that you have a persistent linked list. You're trying to add a node. You manipulated the persistent memory in some way. Basically, normally you need to do these updates in an atomic way, right? Otherwise, you would have an inconsistent state. If the system crashes, for example, in the middle, you may have a node that's connected over here, but that's not connected over here, right? Because you've done the persistent update, right? This is actually true in volatile systems also, but in volatile systems, it's not that bad because your data structure, you can reboot the system and you can rerun the code, for example. So that's why rebooting actually helps when you have volatile memory, because the updates that you make do not necessarily get directly propagated. Sometimes you're not even manipulating the persistent data. But when you're manipulating persistent data, some of your updates actually don't get propagated to the disk. And as a result, some of the bugs you may have in your code may not get exposed, at least indefinitely, right? Or if the system crashes, for example, this may not be a problem in a system where you're not directly updating persistent memory very quickly. But if you're directly updating persistent memory, this may actually be stored in your persistent memory. And as a result, even if you reboot the system, you'll basically get a bad linked list. That's the idea over here. So that's the crash consistency problem. This is very well known in the storage community also. And storage community has ways of handling it. The question is, if you actually are manipulating memory using loads and stores, who should handle it? Yeah. So people have thought about this, and they've actually developed some mechanisms. And usually these mechanisms are explicit interfaces. Basically, they put a lot of burden on the programmer. For example, you have atomic code structures. If you want to insert a node, you basically indicate that this is atomic, meaning this code either executes to completion or nothing of this code executes. That's the meaning of atomic, basically. It's all or none. And this is called a transaction also, in other words. Basically, you declare your persistent memory manipulation that should finish in a whole, as a whole, or as atomically, as a transaction. Now, this requires people to rewrite their code to decide where these transactions should be inserted, right? And this limits the adoption of non-volatile memory as persistent memory. And you need to also partition volatile and non-volatile data. So this puts a lot of burden on the programmers, but this is not a bad way to in the end, I think, eventually write programs. People have actually developed mechanisms to discover what should be atomic as well, assuming some part of your data is persistent. So there's actually compiler work that has gone into this too. So let's take a look at an example. I'll go through this relatively quickly. If you want to update a node in a persistent hash table, this is your hash table with non-persistent, assuming volatile memory. So basically, you need to make everything transactional. Don't worry about what this exactly means. You can read the paper again. You need to make the code transactional. You need to make the update function transactional. You need to manually declare the persistent components. You need a new implementation of parts of your program because that needs to be, again, transactional. Third-party code, you need to rely on it potentially, and that can be inconsistent, so that needs to be transactional. And some operations probably need to be prohibited depending on how they work, unless they're overloaded in the language, for example, to be transactional. So basically, you need to think about a lot of things, essentially. And this paper and some other papers show a lot of other things that I'm not going to talk about. So how should we actually enable adoption of persistent memory? In this case, we took the exact extreme approach. So one approach is programmer does the management. They need to deal with everything. The other approach is programmer should not do anything. Right? I believe the right answer is somewhere in between. But it's always good to take the extreme approach in research and say, let's see what happens. Let's push the boundary over here and see what happens. Where can we get? So this is our approach. Essentially, we wanted to have software transparent consistency in persistent memory systems. And if you want to do something like this, basically, programmer writes a program. They don't try to manage this consistency issue at all. So there are no transactions in the program. So the way you actually need to do this is you really need to have checkpoints in the program. And if there's a crash that happens, you need to go back to that checkpoint. That's the idea. It's a very heavy-handed approach, but you don't have much option, basically. If you crashed, you go back to the consistent checkpoint that you know is consistent. So you need to take the checkpoints at appropriate places also. That's one issue also, like where do you take the checkpoints? So that's the idea, basically. So, and this, to enable this idea, you need to introduce a new hardware-based checkpointing mechanism, because if you do this in software, it's basically too slow, and a lot of overhead comes in. And so the idea is to have checkpointing. I'm not going to talk about multiple granularities, but we actually have a hybrid memory system with DRAM and a non-volatile memory over here. I need to overlap the checkpointing and execution to reduce checkpointing latency. This is important. And you need to adapt to DRAM and non-volatile memory characteristics, like similar to what we had discussed in prior lectures. And we showed that if you actually do this well, which requires a lot of complexity, I'm not suggesting this is easy. It's actually very, very complex. And I wouldn't recommend people to do it really in the end, because it requires a lot of complexity on the system design within a single node. What we targeted was single node. But once you start considering outside interactions, for example, network packets, I/O devices, etc., how do you do the checkpointing becomes a huge mess. Because if you're just looking at the program and the system without outside interaction, checkpointing is relatively easy, right? There's a system state that you can reason about. But if your I/O devices are interacting with you, for example, if somebody's typing something on the keyboard, or if you're outputting something to outside, how do you do the checkpointing becomes a huge mess, essentially. And networking clearly actually complicates things even more. So in the end, and people have looked at distributed system checkpointing also, but that is a lot of overhead as well. So if you want to checkpoint the state of a distributed system, imagine a data center. Usually this is done in high performance computing systems where you distribute computation. That's a lot of overhead actually in checkpointing. But in this paper, we considered a single node, and we showed that actually you can perform very close to an idealized DRAM that doesn't have any consistency cost. So the results are promising, but don't ever think that this is easy. So this is one idea that you need to really employ. Essentially, you want to checkpoint the program state at some point, or system state. This is not the way to do it, basically. You run the program and then spend some time checkpointing. Basically, it's a very bad, very high overhead way. What does checkpointing mean? Basically, checkpointing is really storing the updated memory state somewhere. Updated memory state because you don't want to store the entire memory state somewhere. You just need to you just need to store the changes incremental to the previous checkpoint, basically deltas. compared to the prior checkpoint. I mean, if you want to store the entire memory state, then it becomes unreasonable, right? Usually people checkpoint things you based on the delta compared to the prior checkpoint, essentially. What are the updates that you made during this epoch compared to the prior epoch? So if you do this, this is actually quite costly in terms of performance. So you really want to do this while you run, and then you decide to checkpoint. While you're checkpointing, you want to continue the program. So here you need to be careful because you don't want to update the stuff that you're checkpointing, that you're saving to memory, because you want to be able to go back to the beginning of this epoch if the system crashes somewhere over here, right? So you need to make another copy of data. You need to make this introduces some metadata overhead, because the program that's running over here, if it updates some data, it should not write directly to whatever is being checkpointed or whatever has not been checkpointed yet, right? So you need to make another copy of data in a sense. And then while you're running over here, when you start checkpointing, you start another epoch over here. So basically, this ensures that the checkpointing latency is not on the critical path of running. Hopefully, there may be one case where it could be potentially if you're checkpointing. Anyway, so that's the idea basically. If you don't have enough resources, there may be cases where checkpointing becomes on the critical path. But in this case, it's not on the critical path most of the time, as you can see. So that's the idea, and this actually has a lot of benefit. But you can see that this actually adds additional complexity as well, because now you need to ensure that what you're doing while you're running over here doesn't interfere with the checkpointing over here. That requires copying of data somewhere. And again, this paper discusses a lot of issues like this. And you can actually find the source code online also, if you're interested in doing something in it. Yes, sure. Mm-hmm.
Something here like basically like the compiler figure out like different running points that doesn't internet, so that you can run freely.
You can run freely, meaning without checkpointing, or
You try to find a part of the program that you want to be running together where you don't need to check.
Okay, I see.
You will not like be divided in a position where
I see. Yeah, potentially. I mean, you can certainly, if you can do that, if your code is amenable to do that, you can reduce some of the overheads. Exactly. That'd be nice. Yeah, but we didn't do any of that in this work. Okay. Okay, any questions? So as I said, this is very heavy-handed, and it's an extreme approach, but it's a good way of thinking about this. In the end, I think this shows that maybe the alternatives should be somewhere in between. System should provide some support for checkpointing, and maybe the programmer should direct the system to do checkpointing. We'll see. There's also other work, which I'm not going to talk about. There's actually a lot of literature in this topic. Another topic is, how do you make it easier to exploit persistence? This is actually interesting because if you can take a program that is written for file systems, you have a lot of file operations, and you can convert them to persistent memory operations. That's one way of exploiting persistence, right? But this turns out to be not so great way, because you don't exploit the granularity. So I'm not going to go into it, but people have actually developed methods for helping programmers to automatically identify which parts of a program should be persistent. There are other issues. I'm going into issues that we're not going to go into a lot of detail, but if you actually have persistent memory, this causes some security and data privacy issues. As we discussed, wear out is a problem, right? Endurance is a problem. And someone can actually do wear out attacks, meaning someone can keep writing to your memory and destroy your memory. And people have actually looked at this, tried to prevent it. Not so easy in the end, right? This could also happen in Flash, but Flash translation layer tries to manage it. But in the end, if you're doing so many writes to your storage, eventually it's going to get exhausted, right? The lifetime is going to, the endurance is going to get exhausted. So this is a tough problem with memory that wears out in general. Hybrid memories can also have performance attacks, as we will discuss soon. Yes. Which one? The persistent memory? Yeah, so that's another question that we will come back to later on. But yeah, so far the assumption has been, yes, you're using a virtual address space. Yeah, but I think, Not necessarily. Oh, you mean the single level store, unified interface to all data? I mean, not necessarily, right? Because your virtual address space you can always increase the size of your virtual address space, right? Yeah, it has some problems, yes. But basically, I think what you're getting at is very good. If you have a lot of memory, huge amounts of memory, or huge amounts of data that you can address, how do you manage it? Do you really need the virtual memory as we know it today? And do you do page-based translation? Because that leads to huge overheads, right? Now your page tables become huge. You have to go through address translation and everything. If you know a lot about your data and memory, why not actually manage it directly physically? Right? And people actually ask that question. And there are works that look at essentially directly accessing memory without going through the virtual memory subsystem. And I believe non-volatile memories actually make it much more compelling to do so. Yes.
So, there are way out problems.
Okay. Yes. Essentially, yes. People have developed lower overhead but similar mechanisms to do vary leveling. It's called vary leveling. In SSDs, you try to vary level, as we discussed in an earlier lecture. People have developed simple mechanisms to do vary leveling. But again, even when you do that, you have limited endurance, right? You need to do a lot of buffering, etc., and then it becomes actually more complex. Okay, so performance attacks we're going to talk about in the next lecture, but essentially with hybrid memories, you can lead to performance attacks if you're actually moving data a lot between the memories. And then one issue that comes up that doesn't come up at least as badly in DRAM as data is not erased after power off. So if someone steals your persistent memory device, they can get access to your data, right? If it's not. So to solve these issues, people have proposed mechanisms to encrypt the data. But now if you go encryption, it's a lot of overhead, right? Whenever you need to decrypt the data to operate on the data coming from a persistent, well, the non-volatile memory device, you add additional latency. So people have been looking at computing on encrypted data using homomorphic encryption or different encryption techniques, but this is not there yet. There's a lot of overhead when you want to do computation on encrypted data. It's a good research direction, but unfortunately, there are lots of overheads in that. So this is very interesting, I think. I mean, this sort of thing actually exists in DRAM also to a limited extent. How many people know about cold boot attacks? Yeah, these are attacks that people have demonstrated. This is actually very related to what we had talked about on data retention. As we said earlier, some DRAM cells can retain data for hundreds of seconds, right? So people have developed these attacks. Let's say someone steals your device. They want to figure out what's going on in DRAM. They want to look at find out your private keys, for example, that have come to DRAM. So they basically want to get your DRAM, inspect the entire memory, and they have the entire time in the world to be able to do that. And you're some important person, you have some critical data in your phone, right? Let's assume that, that's the scenario. I don't think I have that on my phone, so I don't need to worry about this. But let's assume that's the case. So people have shown that they could actually freeze the DRAM to very low temperatures. What does this do? Basically, that increase the retention time of the DRAM, right? That's why it's called the cold boot attack. They basically freeze the DRAM to very, very low temperatures. This way you ensure a lot of the data is not going to leak quickly. You plug the DRAM to some other device that you have complete control of, and then you basically read out the data. That's the idea. So that's cold boot, essentially. You can read papers related to it. Maybe we'll assign something in the future. But this is a way of actually taking advantage of the data retention characteristics of DRAM that we have discussed. And people have thought about ways of preventing it. Encryption also helps us, right? If you encrypt all of your DRAM and decrypt it, as long as you don't lose the private key somehow, this should be okay. But then encryption and decryption has a lot of overheads, as we have discussed. But people are still looking into this and computing on encrypted data issue. So this problem becomes much worse with non-volatile memory based. Yes. Mm-hmm.
Yeah, probably becomes very possible. Anything bigger than
mm-hmm. Yeah, absolutely, absolutely. NVM is certainly bigger than DRAM, and also if you're directly manipulating data, you have the private key stored in NVM. So yes, certainly. I mean, this problem already exists in flash devices. If you actually lose your flash device, you basically lose privacy, no question about that. But flash devices are actually, again, easier because if something is really critical, encryption is not a bad option in flash because of the huge latencies, right? But once you go to MVM and DRAM, starting encrypting those memories becomes basically what you're doing is you're trading off some security with latency, right? If you don't want to encrypt your device, you basically want lower latency, but then you're trading off your security or privacy with that. Yeah, it's good to think about these issues, basically. Actually, with flash memory, there are similar issues. For example, if you're working in a police agency and you recover some flash drives, you want to read them out. Basically, people have developed techniques. This is essentially forensics, right? You can get the devices and you can read from them. And how do you read from them becomes an interesting issue. There's actually a breach of research and very practical research that tries to look at that area. It's interesting. Okay, so to conclude, I think we've discussed a lot of issues in emerging technologies, some of which we focused on more, some of which we focused on less. I think the future is still bright, even though we don't have any technologies that are obviously replacing DRAM or flash at this point. I think we need to do a lot of research in it because I think the benefits are huge, right? You can enable orders of magnitude improvements, and maybe this will lead to new applications and computing systems. People have shown, for example, if you use phase change memory as part of your main memory, you can do extremely fast checkpointing and recovery in high performance computing systems, as opposed to checkpointing and recovering from the flash devices. I think that's an interesting application. Certainly booting up systems can actually become much faster. Maybe these are not new applications, but these are things that can affect people's lives. But I think we need to think across the stack and design enabling systems. And this is actually a truly across the stack problem because really you have devices. These are real devices that are different. And you need to design algorithms for it. People actually design algorithms also. There's algorithms. I mean, we have not talked about, but another way of handling write issues is these issues with endurances, design algorithms that are write minimizing, right? There's research that are going on that is basically especially targeted for these devices to minimize the writes as much as possible. How do you minimize the writes that you're doing to memory? And you can read some papers on that if you search for them. So this is a truly across the stack problem, and there needs to be a lot more work, in my opinion. Now, the good thing is, I think we have already had multiple technologies that have been extremely successful. The closest one is flash. But if you go back in history, DRAM has been similar. Now the question going into the future is, what's next, right? Yes. Potentially, yes, depending on the technology, right? I think that's a bit tough, though, right? Because it's already difficult to replace a low capacity memory like DRAM. If you really want to shift the bottleneck completely to computation, you want a huge amount of memory that can be accessed extremely fast, right? That's going to be, I think, very difficult. Mm-hmm. Yeah. Mm-hmm. Yeah, if you can fit them, yes, that's the idea. I think you still need to be data centric. If you design the compute units together with the memory units, like for example, if you have very large amount of flash memory and you actually do computation next to flash memory, inside the flash memory, then I think we're going to talk about that tomorrow, actually. I think you can actually get rid of a lot of that bottleneck. It's very hard to, I think with the compute-centric paradigm, in my opinion, at least in very, very interesting data-intensive applications, it's very hard to come up with an emerging technology that could fix that issue. Mm-hmm. Yeah, sure. If you're doing memory-centric, I think then you can basically, if you have large amounts of memory, even though it may be a little bit small, you can actually exploit the parallelism inside the memory. Okay, so basically, I think if you're in doubt of a new technology displacing some old technology or finding a new place in space, always refer to flash memory. This is a good example also to give people who are, let's say, skeptics or naysayers. Because there's always people who say, oh, why are you doing research in this topic, right? That always exists. yes, this is a much more speculative area, but we have to do that research if you really want to push the boundaries of systems, right? And that research really starts at the very, very low levels, which is the device levels in the end. There are people actually researching devices that are operating at different ways today. But without the research across the stack, those devices can never be enabled. So it's not just here. You really need to enable it across the stack. Okay. And actually, this flash memory, people were working on flash memory in 1990s. I know a lot of people who worked on flash memory even in 1990s. And some folks were writing proposals to national science foundations, for example. And I know at least one person who wrote a proposal to the National Science Foundation on garbage collection of flash memories, early 1990s, late 1980s. And basically, the reviewer said, this technology is not interesting. It's not even there yet. And we don't believe that it's going to be there in 10 years. Why are you working on garbage collection of flash memories? Reject. That sounds good, right? That's exactly how science should evolve. And it got rejected. Now, go back, go fast forward to today. Garbage collection and flash memories. If you read this paper, you will see a lot, but there are many, many other work on garbage collection and flash memories. And this is a huge research area. Well, it's not a research area anymore. It's in all products, basically. So it's good to think about it, things from this perspective. Like when you're a reviewer, for example, maybe they don't care. And if people give this comments, it makes me think that they don't care. But it's good to think about how wrong you will be 20 years down the road. Maybe that's the mindset people should take when they're actually reviewing papers, right? How wrong will I be 20 years down the road? Is there some benefit of the doubt should I give to this? Or am I totally off? So it's good to have that mindset, I think. Okay, and history has proven many, many reviewers wrong. I have this link here. Maybe I'll put it up somewhere in the end. There are these, I don't know, some number of papers that were rejected by reviewers with ridiculous reviews. And then they eventually went on to win the Nobel Prize because they were fundamental contributions to the field that had enormous impact. Okay, so basically, just because reviewers think that that's wrong or that is worthless or whatever other adjective they may give to it, that doesn't mean that it's that way. I think people still need to do due diligence to research, but there are some comments you cannot address, right? How can you address a comment like, this technology is useless, it's not even there yet? I cannot address that comment, sorry. Yeah. Okay, so there are many other research and design opportunities over here. I think we've covered a bunch of these. I'm not going to cover them, but I will mention this one. I think this is important. This goes back to the question that was asked earlier on virtual memory. And I think this is an area that we need to rethink. With these huge memories that are happening, that are going to be part of your main memory, with flash memory potentially extending your main memory, with this unified interface that we're discussing, or even with larger DRAM, terabytes and terabytes of DRAM, does it really make sense to have the same abstractions we have to access memory? Does virtual memory, essentially, the way we design it, make sense? So if you think about virtual memory, it was developed at a time where there was very little memory in systems. We talked about Chuck Thacker in an earlier lecture, right? This person developed the Xerox Alto systems, and he was actually influential in earlier operating systems as well. Multics operating system was developed. That's where the virtual memory concepts got developed, so that you can manage a very small amount of physical memory and get the illusion that you have infinite or large enough memory. Now, that's a good thing to do because that enables the programmers to not think about managing physical resources. But if your physical resources are already huge, does it really make sense to go through virtual memory translation mechanisms every single time you access memory? That's a good question to ask. Maybe there are alternatives to this. Maybe some data structures will fit in memory, and the programmer can say, okay, it fits in memory, I'm going to directly access them. And the system still manages it somehow without going through all that translation. So maybe there are some side ways to interact with the memory. Maybe you need to rethink a completely different abstraction to access memory. I'm not going to go into a lot of details over here, but this is, I think, happening. There needs to be more that happens in this area. This is a paper that we wrote a few years ago. I think there needs to be a lot more, actually. We need to rethink the virtual memory system, basically. Because if you think about it, it's actually a pretty bad way of doing it. So think about 4 kilobyte pages, okay, 8 kilobytes. Okay, 64 kilobyte, because people are arguing 64 kilobyte pages today, right? Let's pick that number. You have terabytes of memory. What is 64 kilobytes, right? You have, let's say, I don't know, let's do the same example that we had with refresh, right? You have 1 exabyte of memory. I'll exaggerate. How many different, how big should your page table be, assuming your pages are 64 kilobytes? That's a huge page table right there. And you have a lot of latency to manage the page table. So today, actually, we have a memory hierarchy, and then we have a virtual memory translation hierarchy in our systems. So it's so complicated. To manage the memory, you really need to go through multi-level TLBs, page walkers. So there's a translation hierarchy on the side also that people need to design. So there's a lot of overhead. Think about that translation hierarchy as not only a performance bottleneck, especially in your workloads where you're doing a lot of paging and TLB accesses. Maybe you don't have a lot of locality. Usually when you don't have a lot of locality, your TLBs don't work well because they're essentially caches for translations, right? So you're actually having a performance bottleneck as well as an energy bottleneck, right? Just to access memory. You go through another layer, indirection, just to access memory. So with emerging technologies, I think it's a good time to think, but with very large capacity DRAM, that's also a good time to think virtual memory, because we're seeing these issues with very large DRAMs as well. Okay. If you're interested, there's an earlier, in 2020, Nastran gave a lecture on this topic. I believe there needs to be more to come in this area. Any questions? I think in this lecture, I've given you a lot of future research directions as well. Yes? Mm-hmm.
You also mentioned persistent and temporary, and locality and low locality.
Mm-hmm.
I think one word you mentioned was also critical data or less critical data.
Yes, yes.
And I was also thinking myself, like very frequently access data or unfrequently access data. Maybe that's more, I don't know how I understand some of the code that you are actually looping over them all the time. So, and I was wondering, in the paper you mentioned, or any front direction, do they talk about this data criticality or import or utility of the data to allocate on, according to that, to allocate?
Like where to allocate in a hybrid memory, for example? Yeah, I mean, we discussed it last time, but yes, one of the papers discussed the utility aspect. Yeah, certainly. I think utility is an important aspect. That's not a new idea also, that's an old idea. People have developed ideas on if you have small amount of physical memory, for example, and you have different data with different characteristics, you can again allocate data based on the marginal utility that the data brings if you allocate to physical memory. But yes, I think that characteristic is important, certainly. But that just looks at the performance aspect, right? Yeah, I think in the end, yes, you need to take that into account. No question about that. I think so. Yes, it's already happening. The memory managers are becoming more and more complex. Memory controllers are also becoming more and more complex. We're going to see that in the next lecture also. Yeah, but I think that's, in a sense, that's complexity that's warranted because it's a critical part of the system, right? If you actually make the memory manager and memory controllers more complex, but make better decisions, maybe we can remove some of the other complexity in the system, right? Okay.
Where you give the problem the freedom to manage which kind of data you want instead of
Yeah. I mean, that's a different dimension, right? Basically, do you give the program, does the programmer dictate everything, or should there be some system help? in the end, I think there needs to be some balance. Because if you make the program responsible for everything, then most of the programs in the world will not be able to do much, right? That's like 99.5% of the programmers don't even care about what's going on underneath, right? I think that should change over time. But it's also very hard to say, programmer, you do everything. Okay, great. There are no other questions. I think we should take a break right now. What do you think? So let's take I guess, let's come back at, I guess I'll give you a 15-minute break, 14:35. And then we'll start memory controllers. Okay, shall we get started? I think it's about time. Okay, now we're done with emerging technologies. Probably we're not going to revisit them again, but it's good food for thought. Any questions before we move on? Okay, so we'll continue memory controllers. We've been kind of talking about memory controllers all along, but we're going to do a deeper dive on memory controllers here. And remember, we discussed DRAM controllers in particular. We discussed they're difficult to design for many reasons. You can refer to our lecture on that. I think it was last week on lecture 11, right? Now I've updated this figure, so that's the good part. It was updated very recently. So DRAM controllers design is becoming difficult. In the past figure, I didn't have the DMA engine, but it has to be there also. So basically, you have cores, you have GPUs, you have hardware accelerators, you have other stuff, which is actually storage, as we have discussed. Whenever you need to bring data from storage into memory, you go through a direct memory access engine. Whenever you need to bring packets from network to the CPU, you actually go through direct memory access engine and bring it into the memory. So a lot of stuff actually goes through the memory controller. You could argue that that's a bad design choice, but that's how systems have evolved, actually. So a lot of, whenever you need to store something into memory so that CPU can operate on it in a compute-centric system, which is what all systems are today, well, all, let's say, commercial systems are today, you have to go through the memory controller. So in a sense, it's really the center of the world, if you will. And we're making this more complicated also. So essentially, memory controller design is becoming difficult, not only because of just these things that we have discussed, like making sure the memory works in the presence of timing constraints, tracking many resources, handling refresh, managing power consumption, optimizing performance and quality of service. But there are many, many agents that are feeding accesses to memory, requests to memory. And memory is also getting complicated on this end. So this is a real system. I'm going to show you another a real system example. And recall that we discussed this performance function, just the performance function. How do you schedule a request to maximize system performance? And then we discussed an idea that could actually ease some of these issues. And I believe there needs to be a lot more research in this direction. How to design memory controllers that manage memory automatically without humans dictating the heuristics or algorithms. Let the memory controller figure out what is a good decision under different conditions. And that was the idea of self-optimizing DRAM controllers using reinforcement learning. And this is one of the papers that we assigned. How many people read the paper as part of the homework? Not yet? Well, there's still time. And you can actually do the readings anytime, I believe. But I think Mohammed can correct me if that's the case. Okay, so this is one of the reasons I think having automated techniques to manage memory is going to be a lot more important into the future. This applies to emerging memory technologies also, I believe. Okay, and this was a challenge we discussed. And I'm not going to go through this again. These are actually in an earlier lecture. And we also discussed this idea can be applicable to other parts of the memory. Rahul is in the back. He's the first author of this paper that looks at reinforcement learning-based prefetchers. There's reinforcement learning-based flash memory management. And this is also Rahul's work that got the best paper award at Micro this year. And next year, he's going to have another best paper award that I'm going to put up over here. That's the prediction, right? That's called last time prediction. What happened last time is going to stay correct for the next time also. Okay, and then we discussed that this is actually a way of thinking about systems, that more data-driven, self-managing systems. And this is the lecture that you actually saw last week. Okay, so that's the backdrop. Basically, it's already difficult to design memory controllers. Now let's look at a particular aspect of it. If you think about memory control as a shared resource, right? The picture that I showed you is a shared resource. That's another shared resource view that we had looked at. Essentially, we have a lot of shared resources in the system. So I want to talk about the shared resource management and problems with shared resources. But before that, I would like to motivate why we have shared resources. So this picture I've already shown you also. If you look at this, there are two things to think about in this picture. One is most of your system is memory hierarchy. Basically, computation units are a very small part, as we have discussed. And the second is most of the memory hierarchy is shared across the computation units. So there's no exclusive access except for L1 caches and maybe L2 caches that could be private. But if you think about a core today's cores are multi-threaded. Essentially, you're running multiple software threads, potentially belonging to complete different programs in a single core. So even the L1 cache is shared between those threads. So there's not much that is not shared today across different software threads in our systems. So most of it is shared. And this sharing actually leads to a lot of issues. Like security issues is one example. You're running together with some application, and that application is trying to discover what you're doing. Because of this resource sharing, there's not isolation between the resources. That application can time what you're doing and guess what data you're accessing. If that application knows what kind of program you are, maybe you're a program that manipulates private keys, for example, that does encryption, decryption. It can basically figure out what kind of private keys that you're managing if someone is really motivated to do that. And that happens because of the sharing of resources, essentially. Sharing eliminates isolation, right? And once you eliminate isolation of resources, a single thread doesn't get isolated execution on the hardware substrate. You're vulnerable to side channels, timing side channels in this particular example, and someone can figure out what you're doing. Okay. So why do we have resource sharing then? Clearly, this has implications in terms of security. It has implications in terms of performance. But the idea is to instead of dedicating a hardware resource to a hardware context, you allow multiple contexts to use it. And I'm talking about hardware context here. Hardware context is essentially a hardware thread. A software thread can execute on a hardware context, right? So example resource that I shared today, essentially everything is shared, I would say. Functional units, pipeline, caches, buses, memory, interconnects, and storage. In a single core, you have multiple threads that are sharing functional units, for example, right? So why do we have this? I mean, clearly this is good for utilization, right? If one thread is not using a resource, some other thread can use it. And this way you can improve throughput of the system or utilization of the system or efficiency of the system. And this is the common argument. For example, when multi-threading was initially developed in the 1960s, that was the idea, basically. The idea is you have I/O access latencies that are long and the I/O device is not utilized, so have multi-threading so that you can tolerate those latencies and improve the utilization of the I/O device. Simultaneous multi-threading was developed in 1990s. It's called hyper-threading right now by Intel, but it was developed in 1990s with the same idea. You have these execution units. There are 8 of them, let's say. A single thread cannot utilize 8 execution units all the time. Why not have multiple threads running in the program so that you can time multiplex the functional units? So that's one benefit, basically. It improves utilization. And also another benefit is you don't need to replicate shared data. So if you actually have shared data across multiple different threads, if you have private execution of these different threads, isolated execution on non-shared hardware, you need to replicate the data, shared data. But if they're sharing an L2 cache, for example, that data does not get replicated. That's the idea. So that's another benefit of resource sharing. It also reduces communication latency. So if you share data or locks, you can basically quickly access them if 2 threads that are sharing the data are scheduled on the same core, right? And they can access the data in the L1 cache. So they don't need to move the data. Even if one of them is updating the data, they don't need to move the data somewhere else because they're scheduled on the same core, right? So clearly this has another benefit. Whereas if they're actually, if they had their separate L1 caches, when one of them updated the data and the other one needed it, it would need to actually get that data somehow. We're going to talk about that later on when we talk about coherence, etc. But if you're sharing resources, there's no need for coherence in that particular case. And then this is also compatible with the shared memory model, which you program multiprocessors using shared memory, and everyone has access to the same logical view of memory. If that logical view of memory is shared across the threads, why not also share it at the hardware level? We're going to talk about more of these more later on. So that's the benefit of resource sharing. But clearly it has disadvantages. As we discussed, it causes contention for resources. It causes security issues also because of this contention for resources. But when the resource is not idle, another thread cannot use it, basically. You have that's the definition of contention, essentially. If space is not, so this is, there's contention in time and contention in space. The time-space duality is nice here also. Contention time means that when a resource is idle, when one thread is using one resource at a given time, another thread cannot use it, assuming that resource is shared. In space, if you have a resource that is spatial, if the space is occupied by one thread, another thread cannot occupy it, right? That's the idea. It needs to reoccupy it basically somehow. So that means that you need to kick out something that belongs to some other thread. So if this happens, this can sometimes reduce each thread's or some threads or both threads' performance. This could actually be bad for everyone. And thread performance can be worse than when it's run alone. So we're going to see examples of this soon. But this happens in any shared resource. The second issue is it eliminates performance isolation. If you share resources, one of the issues is you optimize your program. It runs nicely by itself. But when it's running with another program X, it doesn't run nicely anymore. You lose some performance because there's some resource sharing that happens, even if you optimize your program. Now, if it runs with another thread Y, then you get even more performance loss. And then you may actually be running your thread, your program that you optimize can be running with many different programs, depending on when it's scheduled and who schedules the programs. And in all of those, you may get completely different performance results, right? This is called performance inconsistency or unpredictability or lack of performance isolation, essentially. Normally, what we would like in general is whenever I optimize my program, I run it on a machine, I have the entire machine to myself, and I get some performance. That's what I would expect. But when I ship this program to the cloud, for example, and some cloud scheduler schedules a bunch of other programs with it, I get completely different performance. In fact, sometimes I may get denied service, as we will see. So when could this be important? I mean, this could be safety, life critical also, right? If you actually are aggregating different applications in a self-driving car, for example, one of them may be playing music or playing a video for the kids who are sitting in the back, and the other one may be managing pedestrian detection, right? If you somehow consolidate them together, why would you ever consolidate them together? Well, cost reasons, right? I mean, that's not a good reason in this particular case, but people actually are thinking about this, right? And if you don't have performance isolation, maybe the video actually denies service to the pedestrian detection, and poor pedestrian is not happy, to say the least. So basically, this sort of issue can be very critical. Actually, this also happens in airplanes, but let's not get into that. So basically, thread performance depends on co-executing threads. And if you have uncontrolled sharing, basically, you don't control the sharing somehow. It's called also free-for-all sharing. You don't change your policies to take into account sharing. This degrades quality of service significantly. It can cause unfairness. It can cause starvation. Some application can be treated very fairly, very unfairly, essentially, and some applications may starve because they may not have access patterns that are favored by the policies that are employed in the controllers. So basically, resource sharing has a lot of disadvantages. So people realize that you need to efficiently and fairly utilize the shared resources, especially when these matter to you. And usually they matter. There may be some cases when these don't matter, but usually they matter. So let's take a look at an example. This is from a paper from 2004. As you can see, I like the slides that they have created. But this paper looks at fair cache sharing and partitioning. And basically, the idea is that thread may be executing in this core. L2 cache is shared. When it's running alone, it needs this much cache space. And it has the reasonable locality over there. When the other thread is running alone, it needs this much cache space. When both threads share, T2, thread 2, doesn't get this cache space. As a result, its throughput significantly degrades. Right? This could happen. This could happen even worse, actually. Some thread may be destroying the performance of this other thread. Okay, any questions? Hopefully these are, yes. When people start designing multi-core systems, they don't really basically take care of this problem. Over time, like this problem is not that bad today because people have designed policies, but first multi-core systems did not have any. They basically used least recently used policies when multiple cores were sharing threads, and that's very bad, clearly. That's a good question, basically. Why didn't people design? I don't know the why. I think it's easier, of course, just to put cores and not deal with the memory system. This is another, I think, in my opinion, more compute-centric thinking, right? Oh, multi-core is good. Let's put some cores, ignore the memory system. Call it a day. No, it doesn't work. And many people have shown that it doesn't work, basically. Basically, it's easy to put cores, but it's harder to think about the implications of what happens in the shared resources. Yes? Yeah, so that's a great question. So we're going to focus a lot on memory controllers. We're going to look at the memory controller level management. But caches, it could be done in the cache controller. There's a lot of cache controller modifications that are done in hardware today to provide some sort of fairness. Utility-based cache partitioning is an example of this, by the way. But you could also imagine operating system allocating data so that threads don't destroy each other's performance. So that this is called page coloring in the operating system. If you do page coloring, you basically limit the contention because the operating system can color the pages such that some indices in the cache belong to some application and some other indices belong to some other application. So it's possible. But it's a bit hard to completely do it in software today because you have limited control. Especially when you go to the memory controller level, you have very little visibility into how the data gets mapped to different banks, for example, and even channels in some systems. Yeah, but that's a very good question. Who does this management, hardware versus software? We're going to look at a lot of software. We're going to look at a lot of hardware mechanisms. The reason is, again, as I said, you don't have a lot of visibility. If you add visibility, once you go into software, you basically cannot react very fast. Especially memory requests are generated on the order of nanoseconds, right? Software can react again on the order of, if you're lucky, microseconds. Yeah. Yes. Mm-hmm. 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 Yeah, I hope so. I think that's a very good point, basically. If you have a system that does both memory and computation, you inherently are forced to think about it that way, right? Because your computation and memory are tightly coupled. You cannot ignore one of them. Okay, that affects your mindset, basically. Okay, so why is this bad? I think I've already discussed it, but it makes programmers' life difficult. An optimized program can get pretty bad performance, basically, and performance varies widely depending on co-runners. You worked really hard to optimize your program, and then you get terrible performance, right? Why would you even optimize your program in this case, right? It causes discomfort to user. An important program can starve, and other bad things can happen. This discomfort level can be, you may die in the end, or somebody may die, right? Of course, I'm exaggerating, but this could happen, right? Yeah, it makes system management difficult. For example, if you're a data center operator, how do you enforce a service level agreement when hardware resource sharing is controllable, right? I don't know what this means. Okay, I need to fix the slide, but when hardware resource sharing is not controllable at the software level, there's some bug in this point. So Geraldo will remind me to fix that bug later on. I don't need to fix the grammar at this point. But basically, you're trying to figure out, you're trying to schedule applications at the data center workload scheduler. You have all these applications that people have submitted, and you're trying to figure out which applications should run together. If resource sharing is not controllable, you may actually put one application that would destroy the performance of another application on the same node, right? And this could happen. So how do you actually avoid this if you don't have any control? Well, what a lot of, especially if you have a service like agreement guarantee that you need to satisfy, right? You signed up this agreement with some customer saying that you're going to get this latency, this throughput, this machine. What do? Basically, you over-provision. You basically say with this application, no other application can get rescheduled. It can get scheduled concurrently. As a result, you underutilize your resources. Now, this has a lot of implications now. You underutilize a machine. What does this mean? You need to add more machines to your system. Your data center grows. You need to add more power budget. You need to add more cooling budget. Essentially, you also destroy the energy efficiency of the world. Right? So basically, by not utilizing resources efficiently, you're making a lot of things worse in the end. Okay, so sharing versus partitioning. You could also partition the resources. Sharing clearly improves throughput. It gets better utilization of space and time. Partitioning provides performance isolation. You get predictable performance, hopefully. You get dedicated space. The question is, can we get the benefits of both in some ways? And the idea that we're going to explore is design shared resources, in particular memory controllers, in this particular lecture, so that they're efficiently utilized, controllable, and partitionable at the same time. So hopefully, the goal is to have no wasted resource, nothing idle, let's say, and quality of service mechanisms for threads. So different mechanisms for different threads, because different threads, different software programs require different sort of quality of service, right? So you need to have some configurability in this as well. So this is an example. Basically, memory system is the major shared resource. We're going to look at shared caches if we have time also. So in the end, you need to rethink all of this over here. Whatever is shared, you need to provide some sort of quality of service. And as we discussed, it's much more of a shared resource in the future. Okay, so this is the problem we're targeting, basically. Threads are sharing the memory system, but the memory system doesn't distinguish between threads requests. I think I've already said all of this. So when multi-core systems, for example, were first designed, different threads shared the resources, caches, memory controllers. And because the control algorithms and the caches and memory controllers and the interconnect were not aware of the threads, they basically caused a lot of unfairness, and aggressive threads actually denied service to others. This is still present in parts of the system, but people are mitigated. For example, Intel introduced, I don't know what they call it, cache allocation technology, CAT. I think it's called cache allocation technology, basically. Can anyone double check this? Is it called CAT, Geraldo? I think it's called cache allocation technology, but basically you can specify how many ways of a cache can be allocated to different different applications. And also their hardware is called CAT, okay. And then there's also memory something monitoring. But basically people are trying to do things in a simple way, but there's some quality of service mechanisms that are added today. Okay, how many people have seen this slide? If you've taken DDCA, you must have seen this slide. But this is, I'm going to tell you what some of the studies that we have done related to memory controllers. We're going to not talk about caches for now, but memory controllers. I think caches are a little bit easier to solve. Memory controllers are a bit harder to solve because caches have limited inputs, agents going through the caches. Memory controller is the center of the world. Everybody goes to the memory controller if they want to access the memory controller. That's why the problem is much harder, actually. So this is what we observed on an Intel Pentium D. This is one of the first multi-core processors, maybe the first multi-core processor from Intel, when you run two applications together concurrently. So this is MATLAB, GCC. We don't need to know what they are, but you probably can guess what they are. Yeah. So this is the slowdown each application experiences compared to when it's run alone on the same system. And this is the slowdown you get when you're run together, these two applications. So MATLAB slows down by 7% when it's run together with GCC. And GCC slows down by 3x compared to when it's run alone. So you could probably say, maybe this is unfair. I don't know. Basically, MATLAB doesn't slow down a lot. So if you dig deeper, what's going on in the system is, this is what the system looks like. So there's actually no cache sharing in this particular case. There's some interconnect sharing, and there's memory controller sharing. So the unfairness is coming from the memory controller. You're running, well, in this case, it's called stream and random, but it's kind of like that. You're running two applications, and the memory controller is really favoring one of the applications. And the red application is twiddling its thumbs and waiting, basically. This doesn't sound good, right? Assuming that you have not explicitly deprioritized the random application. And that's the case over here, basically. We didn't explicitly deprioritize the application. And even if you actually deprioritize the application, there was no way of communicating that information to the memory controller at the time. I'm not sure if it's even communicated today. So basically, the memory controller has an unfair algorithm. So MATLAB and GCC are real applications, but I'm going to show you stream and random results. MATLAB is a very streaming workload. It basically keeps accessing memory in a streaming manner. GCC is less intensive and less streaming. Okay, so let's take a look at, so we did the study with a more controlled way. We constructed these two applications, stream and random. Essentially, stream does this. It copies one array to another array in a streaming manner. Streaming manner in the sense that you still get cache misses, but cache misses are to consecutive cache blocks. So you get a very sequential memory access. If you look at how this index is constructed, you basically go to the next consecutive cache block, whenever you do this copy. So it's very sequential memory access. It gets very high row buffer locality in the DRAM row buffers. And it's very memory intensive because we tried to make every access to memory a cache miss, basically. Does that make sense? So we constructed this, the other application, random, in essentially the same way, except for the access pattern. So here we determined the cache block to copy from here to here, or data to copy from here to here randomly. So you have a random number generator that determines the index, and you copy from a randomly determined index every single time. So this is very random memory access, so you get very low locality, as you can see, but it's similarly memory intensive. Does this make sense? And you run these two applications together. Of course, if you want to do the study right and timing right, you should not form the index over here. You should form the index, pre-compute the index over here, because this random number generation takes a long time in a real system. So to really do the study right, this is just an abstraction showing that index here. The core part of your code should not be actually computing the index, because index computation is different, right? So when you run these two codes together and time them, you find that streaming application actually denies service to random access application, just like MATLAB denied service to GCC. And the reason is, again, the memory controller. So let's take a look at what the streaming application does and what the random application does, what the memory scheduler does. Essentially, you have a memory request buffer. We're going to look at a single bank to make things easier to understand. Essentially, streaming application opens a row. It basically accesses consecutive columns in that row, consecutive cache blocks in that row. So what does the memory controller do? So the memory controller, whenever it needs to schedule a request, it needs to pick between two requests. It prioritizes the request that hits in the row buffer. That's the idea. And if it keeps doing that, and if it keeps getting requests to the same row, it will deprioritize the random access application, essentially. And I could go on forever. Yeah. So that's the idea, basically. So this policy is not aware of the threads, clearly, but it's making some decision based on the row buffer, because a row buffer access is much faster, as we have discussed, than a row buffer conflict. A row buffer hit is much faster than a row buffer conflict. You basically, the memory controller makes a reasonable decision to prioritize the accesses that hit in the row buffer. This is a reasonable decision, assuming that's the only application running in the system and there's no other interference. But this becomes a pretty, let's say, this basically destroys the performance of the random access application that's not getting row buffer hits, essentially. That's the idea. So this is an example of a policy that makes sense in a single core system, but it becomes a performance problem in a multi-core system when you have shared resources. When you don't have a shared resource, it's not an unreasonable policy, let's say. It may not be the best policy to employ, but it's not an unreasonable policy. As we discussed, it may not be the best policy to employ because sometimes you may have some random access, right? You don't necessarily want to do this. You don't necessarily want to keep the row buffer open and also do this sort of prioritization. But okay, let's take a look at some numbers. If you have a row size of 8 kilobytes and a cache block size of 64 bytes, you may have 128 requests of the streaming application service before a single request of random access application. Basically, until the streaming application stops accessing the row buffer, the random access application may not access that bank. Okay, any questions? So this is one of the problems with existing policies. Because row conflict access takes much longer than a row hit access, as we discussed earlier, current controllers take advantage of this fact, and they use a scheduling policy that was developed in the 1990s, and that was actually implemented in many memory controllers. That is essentially a prioritization order. The first priority is given to column accesses, as we discussed, which is essentially row hit requests. And the second priority is given to row accesses, to older accesses. So clearly in the first one, you prioritize column accesses over row accesses. So essentially that's what row hit first means. And the second priority is assuming that everything is equal, meaning you don't have any row hit accesses, or you have multiple row hit accesses. This is the second prioritization level. You pick the older requests first. And clearly, the scheduling policy aims to maximize DRAM throughput, but it's unfair when multiple threads share the system. So why is it unfair? It's unfair because it basically prioritizes threads that that have good row buffer locality, that keep on hitting in the row buffer. Let's assume that we remove that. We get rid of the row hit first part. You get rid of basically, you make it first come, first serve. If you do oldest first, is that fair? I see heads shaking. Why is that not fair? That sounds good, oldest first, right? Older people should always go first, for example. That's another, yes, please.
I think it is fair, but you may lose performance overall. So it's not desirable.
Okay. Anybody else who wants to comment?
Like going back to the first, even if you have, I think even within the same application, like one is streaming and one is and then they need to provide it as a service to the same program, and the user is waiting. By the local share that like have some ad in the stream and then just get enough. I think even within the same program, the whole thing.
I see. I think what you're thinking of is basically a higher level fairness. Basically, one thread may be really important. Another thread may not be very important to the user. Yes, but that's not what I'm asking. That's true. I think we're going to get back to that base because some threads may be more important, less important. We're assuming all threads are equally important right now to the user. Yes. That is true, but let's assume that we gave up that one. So I'm not taking advantage of the row buffer. I've just used oldest first. Is that fair? Yes. Okay, yeah, you go first in the back. Exactly, yes. So that's what I was getting at also. Basically, if you just do oldest first, a very aggressive thread that's generating lots of requests will fill the memory request buffer. And another less aggressive thread that doesn't have a lot of requests will get denied service because the requests that are filled by this aggressive thread are prioritized because naturally they're older. Right? That's the problem basically with oldest first policies in general. Basically, aggressive threads that flood the system get more service in the end. Whereas this poor thread that's once in a while generating requests get denied service because it has to wait for all of these requests that are generated by someone aggressive. You can think of this as a bully, right? You have someone bullying you. Basically, they're very aggressive. You don't get a chance to punch because the system doesn't allow you to punch. Maybe that was not a great analogy, but I tried. Yeah, but essentially that thread is a bully in this case and there's no one mediating that bully. Yeah.
There is a problem. Maybe
No. So I'm not actually thinking about banks. That's true. I'm just looking at one bank over here. Yes, but this issue, there are other issues that come up once you start adding more banks and more channels, etc. But yeah, we're looking at just one bank. So basically, even if you remove the row hit first and lose performance and just use oldest first, it's also unfair. And in fact, with MATLAB and GCC, that's what's happening. MATLAB and GCC, MATLAB is streaming plus it has lots of requests. It's essentially a bully with also streaming access pattern. GCC is poor guy once in a while generates requests and it has to wait for hundreds of MATLAB requests. So this is actually measured in real systems. You can see from the paper, stream essentially loses a little bit performance, but random loses a lot more performance. Yes. So that, yeah.
It's just everything solved.
Exactly, yeah. Basically, things back up and not everything. Well, basically, whoever is trying to inject a request to the memory controller cannot. So they stall. Yeah. So buffer full actually leads to some other issues also in the system. Yeah. So we're going to handle that in some other way later on, hopefully. Okay, so you can see that Yeah, I was going to say something about buffer full. So once a buffer becomes full, actually these aggressive threads, if they're generating lots of requests, they're actually filling out a lot of the buffers in the memory hierarchy. So they're actually causing even more problem than just the memory controller. This problem is happening in the caches, prefetchers, etc. basically. So there's a lot of issues with aggressive threads. Okay, so you can see these are real system results. These are real system results. Stream essentially is a memory performance hawk. We basically said in this paper, we called the memory performance attack. So this was Microsoft virtual machine at the time. I don't know if it still exists. How many people know about virtual PC? I used to be Microsoft's virtual machines, but I guess they don't have much market these days. But basically, Stream is a memory performance attack. And we show that this is a greater problem with more cores. So this is another example. This is a 4-core example. libquantum is a streaming thread that's very aggressive. These other applications are actually not so streaming. And they once in a while inject requests to memory. And they, as a result, they get slowed down a whole lot more, as you can see. These are actually interesting applications. I think it's a network simulator. It's a quantum computing simulator. This is a video application. So there are interesting things here. But basically, essentially, you're vulnerable to denial of service if you don't take care of this unfairness. Some application can be written purposefully to deny service to others. You're unable to enforce priorities or service level agreements. And you also get low system performance. I mean, these two are, the first two are obvious, but the third one may not be obvious. Why do you think you get low system performance? If one application is getting prioritized by the memory controller, overall system throughput degrades as opposed to being fair. Why? Anybody? Mm-hmm. Mm-hmm. Yeah, stall basically. Yeah, basically, what's happening is if one application is not treated fairly, they're stalling, right? As a result, their core is not making progress. So you have 4 cores in the system. That's in this particular example. One application is making progress. It's a bully. The other 3 applications are twiddling their thumbs, waiting, assuming that this application is denying service to the other 3. Right? So basically, you're utilizing your system pretty badly. And once your buffers start getting full, it becomes even worse, actually. So it's a utilization problem, basically. As a result, your system is not just uncontrollable or unpredictable, but it's also low performance. That's why this should be prevented. And this is what we argue in that paper. Okay, I was going to say something else, but maybe I'll leave it for later. So I should remind you that these are actually applications that we don't necessarily want to prioritize. We're assuming that they're equal priority. If you want something to be high priority, maybe this is the behavior you want, right? This is high priority. But uncontrollable system means that I want this to be high priority, but I never get this to be high priority, assuming it's running with multiple applications. The only way you can get this to be high priority is by descheduling, getting rid of these applications. That way you get the performance that you want from there by running this application only in 1 core and leaving the 3 other cores idle. If you don't have a controllable system that says this application is higher priority, so a memory controller prioritizes this application, you basically lose a lot of performance, system throughput in the end to get the service level you want. So again, this is repeatable in many, many studies. So this actually becomes much worse as the system size grows. This is another paper that we have looked at, but this is a network-based system. We're going to talk about interconnection networks. But this is a 64-core system where you have a mesh interconnect. And let's assume that there's a memory controller over here and different applications. There's an application over here, Black-Scholes. It's a stock option pricing application. It's a parallel. It's running over here. And then multiple cores over here may be accessing this memory controller. It could be a streaming application again, right? And what happens is because of the latencies, because of the interference it causes, these cores cause, just to access this memory controller in the interconnect, the other application, the network latency or the latency to access memory can increase significantly, as we show in this paper. So this problem becomes worse as the resources scale significantly. Okay, I'm not going to talk more about this work, but this work introduced the idea of memory performance attacks. And then this is the interconnect version of it, let's say, if you will, but there are solutions that are proposed also. I like Maslow, so I'm going to talk about this here. So we talked about multiple different things being important. But lack of quality of service, as I said, can be a safety and security problem, right? We said safety and security are important. And if you're sharing resources and if you don't have quality of service, you're unable to prioritize the important thing, safety critical thing at the right time or security critical thing at the right time. So this could be actually pretty bad, in my opinion. The alternative is not to share resources, right? Or do something reasonable as opposed to what these papers show in real systems. So not to share resources is also not reasonable because it's extremely costly. So what are we going to do? So how do we solve the problem? Essentially, the problem is because you don't control things. The interference is not controlled in the shared resources. Essentially, we need to control the interference. And in other words, design an interference-aware or quality of service-aware memory system. This applies to all shared resources, actually. It applies to the internet, for example. You need quality of service in the routers, etc. But we're going to look at it from the perspective of the memory controller. But there, whenever you design a quality of service-aware system, there are multiple things that you need to think about. There are multiple things that you want to optimize. One is you want to get high performance, you want to reduce the interference as much as possible in the system. And the goal here is to improve system performance and core utilization, right? To be able to do that, you want to reduce request serialization and core starvation. We're going to look at that. Fairness will help this, but there may be other things that you need to employ. You also want control in the system because in the end, your goal is to provide mechanisms for the system software. So system software says this thread is extremely important because it's safety critical, prioritize it at all costs. You should be able to do that. There should be some mechanisms to enable system software to enforce quality of service policies while providing high system performance. So as I said, this is actually quality of service or performance optimization is really easy actually if you don't care about system performance or cost. You basically dedicate 1,000 core system to a single threaded application. That's it. You wasted a lot of resources. So it's possible to get what you want, but at very high costs. So that basically is not solving the problem in the end. The problem is really you want resource sharing at the same time you want controllability and high system performance. And then the third question is how do you make the memory system configurable and flexible? Because again, you don't have a single goal when you're actually scheduling workloads on a system, right? Sometimes you care about fairness, sometimes you don't care about fairness. Sometimes the workloads are designed to work together because they're multi-threaded. Maybe fairness is not as big of an issue. We will see that's not necessarily correct later on, but maybe it's not as big of an issue, which is true actually. So basically you want some configurability in the system. And there could be very strict performance guarantees with hardware accelerators, for example, as we will see. So you want a system that's configurable or flexible, not optimized for a single target metric. So if you're optimizing for fairness, then you have to bake in the definition of fairness also, right? What is fair? This has actually occupied many people in the world. What is the definition of fairness? And there's a lot of literature in economics, for example, on this one. And there's certainly literature in computing systems as well. So you cannot actually decide fairness on behalf of the user because the user may have a complete different idea of fairness than what you bake into hardware. That's why a system needs to be configurable. Okay, so let me talk about two different approaches, and then we're going to look at examples from memory controller. So there are two interesting approaches, and these are complementary approaches whenever you're designing a quality of service aware system. The first approach is to make each of the shared resources, smart, meaning answer these questions for each of the shared resources. Design each shared resource to have a configurable interference control and reduction mechanism. So you have to identify all of the resources, memory controllers, interconnects, caches, buses, etc., SSD controller. All of them needs to be quality of service aware. And put them together and hope that your mechanisms work well end to end. Unfortunately, that doesn't also happen. Basically, you need to have some glue logic, coordinate between those resources also. The second one is a completely different approach. In this case, and it's an extreme, in this case, you keep each resource free for all. You don't design any quality of service mechanism inside the resource. Your caches are LRU based. Your memory control is FRF-CFS based. Your interconnect is some oldest first based, etc. But you reduce or control interference by doing something else outside the boundary of the resources. And here you can control injection into the resources, for example, or you can control data mapping. And this could be powerful. For example, you have resources, memory system, and you have sources that are injecting requests into the resource, and you control how much source each of the cores can inject into the resources. We're going to talk about that. This is source throttling, for example. Or you can try to do your data mapping such that interference is reduced. This, again, software can do that in the caches or memory controllers. You can try to schedule threads such that they don't interfere with each other. You know that two threads have exactly the same characteristics and hope that they're not going to destroy each other's performance, and they're going to get good performance levels if they are scheduled together on a system with shared resources. So in this case, basically, you can get away with not modifying your resources. But in the end, this is very difficult to do completely. So in general, it's best to combine these two approaches. So we're going to look at especially memory controllers in this lecture, but hopefully, I don't expect that this topic will finish by the end of today. So hopefully we'll look at some of the other mechanisms also, because in the end, you have to complement things. Especially, I think source throttling and data mapping are quite important, but thread scheduling can also alleviate a lot of the issues. But alone by themselves, I think this is not easy. If you look at smart resources, you need to design all of these resources to be quality of service aware. But when you put them together, they require some coordination. We're going to talk about that also. So alone, this is not easy also. This way, you can more easily coordinate things. Okay, any questions? So these are two high-level approaches to quality of service. Anytime you see a shared resource, this is actually a reasonable way of controlling it. Yeah, for example, I like this Tanem bar next door. How many people know about Tanem bar? That's the coffee shop next door, right? There's a revolving door. If you use that revolving door, you may have a quality of service problem, right? And I've experienced this quality of service problem if I arrive at that point, at that revolving door in the wrong time, right? If I arrive at over there, if there are 20 students in front of me or 20 people in front of me, then basically I get bad quality of service from the revolving door, right? How do you solve that problem? Well, make the revolving door better. Have higher bandwidth, have some quality of service, or you can have injection control. Maybe the block of 20 people should basically let blocks of smaller people to go, right? This happens also in any queue, essentially. Anytime you have queuing, this happens. But this is an example of a shared resource. Okay, so there are fundamental interference control techniques in the end that are applicable to any shared resource, actually. We're going to talk a lot about the first one. Again, the goal is to reduce or control interference in the shared resources. Memory is a particular example, but you can employ prioritization or request scheduling to reduce and control interference. As I said, we're going to talk a lot about that. You can do data mapping such that you reduce the interference. We're going to talk about that, hopefully. You can throttle the sources, as we have just discussed, or you can do application and threads scheduling. We're going to focus a lot on this one, but don't think that these are not important. These are also quite important, except there's more work in this area. And this is a bit, how should I say? It's a bit of a harder problem, I would say, because here you're given some requests. You have no control of where the requests are coming. You basically are told, deal with it, right? That's what the memory controllers face today. Deal with all of these requests, right? Of course, you can complement this with source throttling. Then that makes the problem easier, right? If the memory controller says, okay, I'm not able to deal with it, it can tell core X, get rid of your request from me. That would be nice, actually. Now we're thinking about more combined solutions, right? But if the memory controller doesn't have that option, it's just deal with it. That makes the problem much more complicated. And that's why this is a harder problem, in my opinion, fundamentally, compared to these three. I mean, application thread scheduling is kind of similar. You're given some bunch of applications and you're told to deal with it. That's another possibility. But I think this is, as we will see, this is not an easy thing to do. It's very coarse grain in the end. It's very hard to figure out applications that can run well together in all of the resources that they interact with each other. Okay, that's the reason why we are focusing on the first one, because this is fundamentally a harder problem. But as I said, you can actually ease the problem by combining different solutions. Okay, so we're going to talk about other quality of service techniques, hopefully, in the next lecture. But if you're really excited about it, you can take a look at some of the things that are coming. And we're going to talk about that curve later on. I don't have time right now. But we're going to talk about an idea called memory channel partitioning, for example. You can partition channels across applications. And this is a good idea in general, but unfortunately, it's not a scalable idea because you can the number of applications that you're running in a single node is much greater than the number of memory channels that you have. So I can reduce interference a little bit with this idea, but you need to employ other techniques also. And this is what happens usually with the data mapping techniques and application thread scheduling techniques, and to some extent with core source throttling techniques. These are not good enough by themselves. So they have to be complemented some way. And essentially, when they don't work very well, you're back to a memory controller dealing with it. Okay. So we're going to talk about also I/O interference briefly, because that's also quite important. Okay. Any questions? So hopefully yeah, go ahead. Mm-hmm. 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 Someone who can game the system, let's say. Yeah. Mm-hmm. Mm-hmm. Yeah. So that's a very good question. And then you need to be careful, right? Is the mechanism that you provide gameable in some sense? Will it lead to some other denial of service or quality of service issues? I think there you definitely need to be careful. So from a security perspective, whenever some mechanism is always known, some people will develop attacks to overcome this. And yes, I think some of these quality of service mechanisms can potentially be vulnerable to that. Yeah, we'll see. Mm-hmm. 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 Yeah. Mm-hmm. 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 Yeah, I agree. And we'll discuss some of that later on. So if you're static, for example, if you partition memory statically, once the behavior changes, you basically are vulnerable to the similar problems that you're trying to avoid. So yeah, these mechanisms all need to be dynamic. I agree with that. Mm-hmm. Mm-hmm. Yeah. Yeah, we'll see. Yeah, you'll see some incarnation of those ideas. Yes. Yes, please. Are they sending the requests? So we're going to assume that we know which threads are sending the requests. I think that's simple information that you can communicate to the memory controller or caches. Yeah, that's a good point. Okay, so basically, as we have discussed, the function of the memory controller is to resolve memory contention by scheduling requests coming from cores. And the key question that we're going to look at is, before we looked at system performance, right, reinforcement-based memory controllers, but we also want high fairness to applications, and we also want configurability to system software. That's what we're going to target right now. So it's a more complicated problem than just performance, right? So this answers your question, I think. Memory controller needs to be aware of threads or hardware contexts that are executing in the cores. I think that's necessary. So there needs to be some space. Okay, I'm not going to talk about these, but there's a lot of work in this area. This is, you can take a look at this as a summary, let's say. This is the abstract of what's come. We're not going to cover all of them, no. But for example, there work on criticality-aware scheduling. That's important, I think, which we're not going to talk about. But let's talk about some of the first solutions that we had developed when we first figured out this was a problem. And this is the idea of stall time fairness. So basically, I've already given you the problem. You have this unfairness. You have slowdowns that are completely unfair. Our initial idea was to actually solve the problem using a different definition of fairness. So oldest first, you can say there's some fairness to it. Yes, oldest first fairness. But in the end, it doesn't take into account performance, overall performance. We wanted to come up with a fairness metric that takes into account overall performance or slowdown of applications. And this is how we define the goal. If you have threads that are sharing main memory, they should experience similar slowdowns compared to when they're run alone. So this was our definition of fairness. You could argue that this may not be the best definition, and I agree with that. Actually, later on, we actually changed this definition of fairness in a different way. Basically, we wanted to minimize the maximum slowdown of any thread in the system, and I believe that's a much theoretically also a better definition of fairness. I'm not going to go into theory over here, but there's a lot of interesting theory that you can discuss over here as well. But this was our definition, and it's kind of intuitively not terrible, right? It's better than basically oldest first, which provides no guarantee in the end in terms of slowdown. So the intuition was that we're trying to ensure cores make proportional progress, proportional slowdowns essentially compared to when they're run alone. And hopefully this will improve system utilization as well, because cores are not, none of the cores are left behind in a sense, right? And the idea is, of course, how to implement this basically. Memory control estimates each thread slowdown due to interference and schedules requests in a way to balance the slowdowns. And that's what's detailed in this paper. I'm not going to go into all of the details, but essentially this is the definition. A DRAM system is defined to be fair if it equalizes slowdown of equal priority threads. That's important, this equal priority, relative to when each thread is run alone on the same system. So we're going to look at DRAM-related stall times. This is the time a thread spends waiting for DRAM memory. And then there's two types of stall times that we want to know. One is stall time shared. This is the DRAM-related stall time of the thread when it runs with other threads. There are some core runners, essentially. And then there's some stall time alone, which is essentially the stall time of the thread when it runs alone on the same system. And the memory slowdown is defined as stall time shared divided by stall time alone. It's essentially a relative increase in stall time. This sounds good, right? For example, if the stall time alone is one second for a thread, and stall time shared is 10 seconds, it basically slowed down by 10x. If you have another thread whose stall time alone was 10, and if it slowed down by 1 second, 11 seconds, so it's slowed down by 10%. So the goal of the stall time fair memory scheduler is to equalize memory slowdown for interfering threads without sacrificing performance, hopefully. So the good thing about this metric is it considers the inherent performance, baseline performance of each thread compared to when it's run alone, essentially. And the hope is that it aims to allow proportional progress of the threads. Any questions? Okay, so far so good. So how do you implement this? That's the difficult part, essentially. Basically, the memory controller needs to keep track of stall time shared, which is easy, hopefully, because you're seeing the threads and requests, and you're basically calculating how much each thread is stalling because of a DRAM request, and you're accumulating those cycles. This can be actually done in the core of each thread. The really difficult part is the stall time alone. How do you estimate that? Because you're running together with other threads. How do you get the stall time alone of this thread? Well, you need to do some calculation, probably. Or you can deschedule all of the other threads and try to figure out stall time alone. That's terrible for throughput. And also, it may not be representative because you're really calculating stall time alone for a different portion of the program, perhaps, right? So basically, in each cycle, I'm not going to go into details on how to estimate the stall time alone. I don't have slides, but basically, the idea is to figure out the excess cycles a thread has. So you know stall time shared. You want to, stall time alone can be expressed as stall time shared minus some excess cycles. So there are some excess cycles that happen because of sharing of resources. The question is, when do those excess cycles come in, and how do you calculate that? For example, if a thread has a request and another thread has another request, And if the memory controller chooses other threads, you can increment the access cycles for this thread that is deprioritized because some other thread is accessing a bank. So that's a clear case of access cycle. But of course, it's not easy as easy as just counting the number of cycles that a request spends when it cannot be scheduled due to another thread, because there are a lot of other issues in the memory controller, right? Overlapping of requests, for example, because not every single delay translates to an excess stall time, because some of them may be overlapped. And then there are other issues like state in the memory controller, row buffer locality, for example. A thread can change another thread's row buffer because of the row buffer conflicts. And how do you take into account excess cycles? So this paper talks about some of those issues. There are other issues like write to read latencies, write to read switching. So in the end, you need to keep track of a lot of these things, and it complicates the estimation of those excess cycles. But assume that you've done it. The DRAM controller computes a slowdown for threads with legal requests. Legal requests are requests that can be scheduled. They're ready to be scheduled, basically. So each thread has a slowdown value, which is ST shared divided by ST alone. It also computes an unfairness value in the entire system, which is max slowdown divided by minimum slowdown in the system. And then the scheduling policy looks like this. If unfairness is acceptable, given by an acceptable unfairness threshold provided by the system software, it uses a DRAM throughput-oriented scheduling policy, which essentially could be what we discussed, right? Row hit first, and then oldest first. And then, however, if the unfairness is not acceptable, it's greater than a threshold, it switches to a fairness-oriented scheduling policy. It basically prioritizes the request from the thread that has the maximum slowdown first. Basically, the goal is to reduce the thread that's slowed down the most so that you can reach an acceptable unfairness level. And assuming everything is equal, it uses the remaining prioritization policy parts. Makes sense, hopefully, right? So that's the idea. It's complex to implement, but it's a nice, let's say, way of thinking about it. So how does this prevent unfairness? Let's take a look at the same example. We have random and streaming workloads. This thread is accessing the row buffer frequently, row 0 frequently. This other thread is more random access. Basically, you compute slowdown for each thread, and then you have an unfairness value, which is clearly 1 in this case, and you have an unfairness threshold, 1.05. Basically, unfairness should never reach more than 1.05, hopefully. So let's take a look at what happens. So in this particular case, the unfairness is acceptable, less than 1.05. So the memory controller keeps using the throughput-oriented scheduling policy, which essentially schedules requests that hit in the row buffer first. Okay, that sounds good. That increased the slowdown of the thread that did not get service, even though that had a legal request. And that increased unfairness. So unfairness is still acceptable, so you keep exploiting the row buffer. At some point, unfairness increases beyond the unfairness threshold, and then the memory controller picks the request that goes to some other row. In this particular case, right? Basically picks the requests from the thread, I shouldn't say picks the request that goes to some other row, picks the request from the thread that has been slowed down the most, which is T1 in this case, right? Which essentially causes a row buffer conflict, which increases T0 slowdown compared to when it's run alone, because if it were run alone, it should not get a row buffer conflict, right? So you need to basically take these into account. And essentially unfairness reduces below the unacceptability threshold. And then you go back to the throughput-oriented scheduling policy. You pick the request that's the oldest. That causes another row buffer conflict, which increases slowdown of T1. And then you basically continue with the throughput-oriented scheduling policy until unfairness again becomes unacceptable, at which point you switch back to the fairness-oriented scheduling policy. Essentially, the memory controller works by switching between two different policies, throughput-oriented versus fairness-oriented, based on this unfairness threshold. Make sense? Okay. Assuming you can implement it, this sounds good. Okay, I can keep animating it. And you can see the paper, the results are most of the time that are good. But basically, this is really the first algorithm specialized for fair multi-core memory scheduling. It takes into account things like row buffer. It takes into account things like banks. These are important to take into account, as we show in this paper, actually. Clearly, people have looked at quality of service aware scheduling in networks, for example. This is a very different problem in the sense that if you look at a network router, you're scheduling requests from different flows to a single link. That link is very different from the DRAM system. That's why this this sort of algorithms are really important. So people have been looking at quality of service over a router designed for, let's say, since late 1980s or so. As I said, the difference is you have in a network router, you have a link, you have different flows. This link doesn't have locality. There's no notion of row buffer. It doesn't have the notion of parallelism. Basically, there's no notion of banks. And if you look at the broader memory system, it has no notion of channels also. So that's the difference between network scheduling and main memory scheduling. Yes, please. Yes, this one. Oh, I think it can only increase. Yes, assuming you basically keep looking at a longer program, it can only increase, right? But you can reset it at some point also. That's right, exactly. So in this case, we don't reset, but you may need you need to reset it when you schedule a new thread, right? So in the scheduling quantum, you'll need to reset it. Okay. Yeah. So it provides a mechanism to estimate the memory slowdown of a thread. We're going to look at that later on. This could be useful for performance predictability, because if you can accurately estimate the memory slowdown of a thread, you can basically provide some guarantees potentially, right? You can say my slowdown should not be more than X. And we're going to see that later on, hopefully, if we have time. But in this particular paper, the slowdown estimation is not accurate. Essentially, it has a lot of inaccuracy because we don't take into account a lot of things. Even then, the performance results are actually not bad. Our goal was not perfect quality of service. Our goal was fairness in this case. And these are two different issues, actually. Fairness is very different from quality of service. Quality of service, for example, is much more strict. It says your slowdown should not be greater than 2, for example. We're not trying to do that over here. What we're trying to do is basically keep unfairness in check. So this is good at providing fairness, and the results show that. You can read the paper. And being fair can improve performance. In most of the results, we see that performance improves. Not in all cases. In some cases, performance degrades because you lose a lot of row buffer locality, right? If you keep switching between the row buffers, you lose a lot of row buffer locality. Bank level parallelism sometimes degrades. So basically, in general, being fair improves performance, but not always. Remember, we're trying to increase the core utilization by being fair. That's the major benefit. But there are also downsides. You're losing memory throughput because you're not really maximizing the DRAM row buffer utilization. So being fair can improve performance, and most of the time it does improve performance, but not in all cases. Sometimes it degrades performance. So the downsides, as we said, it sometimes degrades performance. That should be there perhaps, but it doesn't handle all types of interference, and we will see that. For example, it doesn't take into account the write to read interference, which is actually a big deal in modern memory controllers. It doesn't take into account bank level parallelism destruction, as we will see in the next work. Basically, there are a bunch of things that it doesn't take into account. It's very hard to take into account everything also. So if you really want to perfectly estimate the memory slowdown of a thread, you have to simulate the entire memory controller. So you have to really have a concurrent simulation of what should have happened if the thread were running alone. And clearly that's expensive, right? We talked about simulation of memory controllers. That's expensive in software. That's also expensive in hardware because you really need another memory controller on the side. We're trying to avoid that. And if you're trying to avoid that, you cannot perfectly estimate the slowdown. And you basically need to ignore. And because of this, again, it's complex to implement because of what I said. It's not easy to estimate this. And slowdown estimations as a result can be incorrect because you don't take into account everything, and you cannot take into account everything because you don't actually simulate the memory controller. So even then, this paper showed that you can improve performance significantly and get rid of a lot of the unfairness in the system. This is an example where being fair actually on average improves your performance. Any thoughts, questions? Basically, we're going to incrementally build on these works. This is the first attempt. It sounds like a good attempt, but there's a lot more to discover. Okay, let's talk about the other one. And probably this will be the last thing we talk about, and we're going to talk about. So tomorrow, what we're going to do is a research lecture. So we're going to cover a bunch of research papers. Hopefully, it'll be interesting. And then next week, we're going to continue on memory controller design. So we're going to explore a lot of interesting ideas in memory controllers. And I'm going to give you some anecdotes from industry also. But let's talk about this one and hopefully finish this one today. So while we were doing a lot of these studies, we realized that there are other things that are happening in the memory controller because of memory interference. And this is actually very interesting and still very exciting to me. Basically, we discussed about latency tolerance. Right? Processors actually try to tolerate we have long latency DRAM. Processors actually do a lot of techniques to tolerate those requests. They basically generate multiple outstanding requests. They basically exploit memory level parallelism. We've talked about, well, you've hopefully taken a class about out-of-order execution. In DDCA, we covered out-of-order execution. You have multiple requests outstanding from the caches from a single thread. We've talked about run-ahead execution very briefly in an earlier lecture. So essentially, you try to generate many requests so that not a single different requests can be serviced in parallel, and their latencies are overlapped, so that you stall only once for many requests, as opposed to stalling once for each request. So this sounds good. Now, this is effective, of course, only if the DRAM controller actually services the requests in different DRAM banks in parallel. But when multiple threads are sharing the DRAM controller, and DRAM controllers are not aware of this parallelism that should be serviced in parallel in different banks, the controller can service each thread's requests serially and not in parallel. So I'm going to demonstrate this with a picture. So let's take a look at a single thread. We're going to look at a toy system with 2 banks only. A single thread computes. It generates 2 DRAM requests. They're mapped to 2 different banks, as you can see. Ignore the row numbers. They're not relevant here. But basically, the memory controller gets the first request, starts it, and then it starts the next request in the next memory cycle. And both requests are being serviced in parallel in the 2 banks, and the thread stalls, of course, because it's waiting for data to continue. And then once both requests go back, the data goes back to the core continues computation. Now, this sounds good. This is a good case where the bank access latencies of the 2 requests are overlapped in the banks, and the thread stalls for approximately 1 bank access latency, assuming the bank access latency dominates the complete memory access latency, right? Okay. Now, let's take a look at what happens when you execute 2 of these threads, A and B, that do essentially the same thing. Both of them generate 2 DRAM requests, and I've color-coded them. And these requests happen to arrive at the memory controller in this order, and assume that the memory controller schedules requests in first come, first serve, oldest first order. It first takes thread A's request to bank 0, schedules it, and then takes thread B's request to bank 1, schedules it. And these 2 requests are being serviced in parallel. Both of the threads stall. And then the memory controller takes thread B's request to bank 1. Thread B's request to bank 0. Once thread A's request to bank 0 is done, the memory controller takes thread B's request to bank 0 and schedules it. And then the second request is done in bank 1. Then the memory controller takes thread A's request to bank 1 and schedules it. And both of the threads continue stalling. Now, this looks okay. And in the end, the request gets completed and the cores start executing when both of their data items arrive. So essentially what happened in this case was bank access latencies of each thread was serialized, and each thread stalls for approximately 2 bank access latencies as opposed to 1 when each of them would be running alone. So the question is, can we do better? And the answer is yes, as we will see, right? So this is essentially 2 threads running, and they generate the same requests. The memory controller gets them in this order. The memory controller takes the first request from thread A and schedules to bank 0. And then the memory controller realizes that if it takes the next request, it will destroy the parallelism of this thread. So it basically looks at its queue to see if it can actually parallelize another request from thread A. It finds it over here. So instead of taking thread B's request and scheduling to bank 1, it takes thread A's request and schedules it to bank 1. That way, thread A has both of its requests being serviced in parallel. It stalls. Thread B also stalls, and poor guy doesn't have any requests being serviced. But its request gets start serviced after thread A's requests complete, and then thread B's request gets scheduled to banks. Now, what happened here was thread A's requests were prioritized over thread B's and serviced in parallel, but thread A was able to start its computation much earlier. It stalled only 1 bank access latency for 2 requests. Thread B stalled 2 bank access latencies for 2 of its requests, but it didn't lose anything compared to when it's run alone. So basically, that's the idea over here. If you actually try to preserve the bank level parallelism of each thread, you can improve overall system performance. So the average stall time of the threads is 1.5 bank access latencies as opposed to 2 bank access latencies. And both of the threads had their requests serviced in parallel, except this thread needed to wait for A's request to be serviced first. Does that make sense? So overall system throughput improves this way. And this is just a toy example. If you actually have many cores, the paper as an example, more complicated example with many cores and row buffers, etc., you get even better results. As I will show you also in a little bit. So that's the idea over here. Can we somehow preserve threads bank level parallelism? So the parallelism over batch scheduling is built on 2 principles. One is parallelism awareness. And I've just given you the idea for that. Basically, if you schedule the request from a thread to different banks back to back, you preserve bank level parallelism actually. So, but the problem is this can cause starvation. So we employ a second principle, which is a known principle actually. It's called request batching. So as far as I know, this was not done, but request batching was done in I/O systems, for example. So the idea is why can the first one cause starvation? You basically prioritize the thread's request, and the thread keeps generating requests, right? It's not a system where basically this is a dynamic system. The thread can keep generating a lot of requests, and soon you will figure out that you're servicing that thread only, right? So that's what we want to avoid also. We still want fairness and quality of service in some sense. So basically, the second principle is request batching. We're going to group a fixed number of oldest requests from each thread into a batch, and we're going to prioritize that batch and form a new batch when the current batch is done. So basically, service the batch before all of the requests. So this gets rid of the starvation. It provides some sort of fairness, and it's actually a very good substrate to build fairness policies in. It also allows parallelism awareness within a batch. So let me give you a pictorial example. Again, cooked up, simple. You have a bunch of requests from different threads that are waiting for some reason because there are some other requests in the bank service. But you form a batch. Let's assume this is our batch. And then you basically prioritize thread 0's request first. Thread 0's requests are serviced in parallel. In the meantime, thread 2 keeps generating requests, but they're not entered into the batch. So the batch is prioritized. And then thread 1's requests are serviced in parallel. And then thread 2's requests are serviced in parallel. But notice that thread 2's requests outside the batch are not serviced because they are too late, too bad for it. And then thread 3's requests are serviced in parallel. And then the memory controller forms a new batch and schedules that batch. This guarantees starvation freedom. And again, this is an old idea that's employed in disk systems, and it's a good idea to think about. But this is just one idea among a collection of many, many ideas where you can actually get quite creative, I think. So that's the idea. So the question is, how do you implement it? Request batching, and there are 2 components, request batching and within batch scheduling. Let's take a look at request batching. This is actually easy to implement. Each memory request has a marked bit associated with it. And the way to form the batches is important. The memory controller marks up to some marking cap oldest requests per bank for each thread. And the mark request constitutes a batch, and it forms a new batch when there are no mark requests left. This is one way of forming. You can actually have multiple batches also, but let's ignore that for now. We're keeping simple. And the mark requests are prioritized over unmarked ones. So there's no reordering of requests across the batches. There's no starvation, high fairness, so forth. Then the question becomes, how do you prioritize requests within a batch? This is where parallelism awareness comes in. Actually, you can use any existing DRAM scheduling policy. You can use FRF-CFS, but we want to avoid that. So we don't want to destroy row buffer locality. We want to get row buffer locality, but we also want to preserve intra-thread bank parallelism. So we want to add this idea of servicing each thread's request back to back. So the idea this paper introduces ranking of threads. Scheduler introduced a ranking of threads when the batch is formed, and higher ranked threads are prioritized over lower ranked ones. And ranking of threads actually improves the likelihood that requests from a thread are serviced in parallel in different banks, because you use the same ranking across all of the banks. If you use the same ranking, thread 0 is prioritized across all banks. Hopefully, thread 0's requests are serviced in parallel, and then thread 1, and then thread 2, and then thread 3, and then thread 4, just like I showed you earlier. Okay, then the question is, of course, how do you form that ranking? Now, let's take a look at 2 different rankings. So this is thread A and thread B, color-coded. Basically, this is the baseline. The key idea is to rank thread A over thread B. So this is what it enables. Thread A's requests go first, thread B's requests go next. As a result, overall system throughput improves because thread A gains performance compared to this baseline. Thread B doesn't lose performance. Right? Okay, so ranking scheme actually affects both system throughput and fairness. And ideally, we would like to maximize system throughput, minimize the average stall time, and minimize unfairness at the same time, or equalize the slowdown of threads, assuming we're doing stall time unfairness. So maximizing system throughput means minimizing average stall time of threads within the batch. And minimizing unfairness, it turns out, actually is a similar thing. Ideally, you would like to service threads with inherently low stall time early in the batch. Why? Because inherently low stall time means the thread is not memory intensive, right? So let's assume a thread, basically delaying a memory non-intensive thread results in high slowdown. Assume two different threads. One has a stall time of 1 second, another has a stall time of 10 seconds. If you delay both of them by 1 second, which one slows down more? The one that's light, meaning not intensive, right? The one that has only 1 second to execute. The one that inherently has 10 seconds stall time, if you delay it by 1 second, it loses performance by only 10%, right? So heavy threads are actually the ones that are not to prioritize. So we were discussing these oldest first. Oldest first is actually doing exactly the wrong thing, because it's really slowing down threads that are not supposed to be slowed down because it's really delaying things. So the same amount of delay affects a non-intensive thread much more compared to an intensive thread. So that's the insight over here. So this is actually, there's a lot of scheduling theory that has looked at how to maximize throughput, etc. I'm not going to go into the theory of it. You can read the paper that talks about some of this. But you want to really do shortest stall time first or shortest job first ranking. And again, this paper provides some reasoning from a totally different domain. So these people are actually trying to maximize the throughput of production of a system. Essentially, you're talking about factories. You're sending requests to different factories, and different requests take different amounts of time. How do you actually maximize the throughput of essentially the production of different things? So you can read that paper if you're interested. It's very theoretical, but shortest job first actually provides optimal throughput. So the idea here is to have the controller estimate each thread's stall time within the batch and rank the threads with shorter stall time higher. So that's what the paper introduces, shortest stall time first ranking. Basically, we're going to look at two things. We're going to look at maximum number of mark requests to any bank. This is the max bank load. And we're going to rank the thread with lower max bank load higher. And we're going to look at total number of mark requests. And this is to break ties. Let me give you a pictorial example that's going to clarify things a lot. This is what we have: 4 banks, 4 different threads. Let's compute these values for each thread. So thread 0's max bank load is 1. The maximum number of requests it has to any bank is 1. Total load is 3. You can count 3 requests. And memory controller can count these easily. Thread 1, max bank load is 2. So it has 2 requests to bank 0. So its stall time is inherently expected to be higher in the baseline, right, when it's run alone. But total load is also 4, as you can see. Thread 2, max bank load is 2. So it has 2 requests to each of these 2 banks. So max bank load is 2. Total load is 6. Its stall time is probably going to be a little bit higher when it's run alone compared to thread 1. And thread 3 is the most intensive thread. Its max bank load is 5 over here in bank 3, and its total load is 9. So it makes sense to prioritize these threads as shortest stall time first. T0 is prioritized over T1. T1 is prioritized T2 because its max bank load is the same, but total load is lower. And then T2 is prioritized over T3. Why? Because we expect that a thread with a smaller max bank load is going to have a shorter stall time. And we want to rank that thread early. And we use the max total load as a tiebreaker. Let's take a look at the scheduling order here. So this is time. This is the baseline scheduling order. T0, if you use the baseline scheduling order, this is first come, first serve. Ignore the row buffer. The paper is an example with row buffer. Thread 0's last request is serviced after 4 time units. Thread 1's last request is serviced after 4 time units. Thread 2's last request is serviced after 5 time units. And thread 3's last request is serviced after 7 time units. So if you average these out, 5 bank access latencies. Now let's take a look at PAR-BS, parallelism-aware scheduling order with the ranking that we proposed. Thread 0 is ranked. Basically, this is the ranking order. So thread 0's requests go first. They're serviced in parallel. Nice. Its stall time is 1. Thread 1's requests go next. It's like Tetris, kind of, right? And its stall time is 2. Thread 2's requests go next. Stall time is 4. Thread 3's requests go next. Stall time is 7. Now, in this nicely cooked up example, you can see that average bank access latencies is 30% lower. This is within batch. Now, across batches, things become more complicated, so you don't get this high performance improvements clearly, because across batches, there are other stuff that's happening. And this is the scheduling policy. I think we're almost out of time, but basically you can actually use this as a prioritization order, mark request first, that's batching. And then you need to do parallelism awareness within the batch scheduling. So higher rank thread first is the third priority order, because there is always a tension between bank level parallelism and robo for locality, unfortunately. The paper discusses it a lot more. So you can exploit robo for locality as well as intra-thread bank parallelism. It's worth conserving. Basically, you don't keep the DRAM idle. If there's a request that's waiting for a DRAM bank, it gets scheduled because it's a prioritization order, right? You don't throttle things. And marking cap is actually important. This is what the paper discussed. If you have a too small cap, your batches are small. It destroys robo for locality. If you have too large of a cap, your batches are large, and a memory non-intensive thread waits a lot for the stuff that's in the batch. So there's also an interesting thing over here. There are many more trade-offs. And the hardware cost is small, and the performance actually, as you can see, is quite good compared to STFM, which is the state of the art. And you can see that first ready, first come, first serve is pretty bad in terms of unfairness. First come, first serve is also bad. This is network fair queuing. You apply networking principles. It gets actually very bad with large cores because it doesn't take into account robo for locality and bank level parallelism. It's worse than first come, first serve. And STFM is actually quite good, as you can see, but it's actually very complex to implement. It doesn't take into account bank level parallelism. So PowerBS was the best schedule at the time. And also it improves performance, as we discussed, because you're both improving stall times because you're taking into account bank level parallelism. You're also scheduling shortest job first. You're improving system throughput. You're also providing better fairness. So overall, this is actually the highest performance and highest fairness scheduler at the time. Let me cover this and then we'll be done. So this is actually implemented in some Samsung SoCs. I don't know if they still implement them. I'm not disclosed as I used to be, but some of the principles are implemented. I believe batching is implemented in some memory controllers also, even though people don't talk about these things. But this is the first scheduler to address bank parallelism distraction across multiple threads. This is actually quite interesting, I think. We designed these out-of-order engines, all of the memory hierarchy, except the memory controller is doing the wrong thing. It's basically destroying all of that bank level parallelism or memory level parallelism. It's much simpler compared to stall time fair memory scheduling, and batching is a nice substrate to provide fairness, and ranking enables parallelism awareness. So these two concepts are quite nice to build on in the future. The downside, as we will see, it doesn't prioritize latency sensitive applications always because they get delayed beyond the batch. So there needs to be some mechanism for this. And we're going to talk about some other issues in the next lecture. I think we're out of time. I haven't checked it, but any questions? Maybe you can leave it for next week because we're going to continue where we left off. Tomorrow, as I said, we're going to have a research lecture. So it's going to be a lot of fun. We're going to cover many different ideas from 2021 to 2022. And feel free to come and ask questions. Okay, I'll see you tomorrow and we'll continue next week. Okay. No, this is not.